Welcome to the sleepy Milky Way. This is a quiet space, a gentle corner of the cosmos carved out just for you, where the universe unfolds slowly and without urgency, where galaxies drift and stars breathe, and the deep, vast architecture of space is explored not with haste or alarm, but with the unhurried patience of a long winter night. The sleepy Milky Way is a channel dedicated to calm journeys through the cosmos, through galaxies and nebulae, through the slow revolutions of planets and the soft pulse of distant suns, through the grand and often quietly astonishing science of everything that surrounds us. Whether you are settling in for the night, winding down after a long day, or simply looking for something steady and warm to accompany the closing hours of your evening, this channel exists for you. If you find something here that soothes you, that slows your thoughts and opens a window onto the infinite, consider subscribing and joining this small, growing community of quiet explorers who drift together through the universe, one slow and peaceful story at a time. There is no rush here, no urgency, no timetable. The stars have been waiting for billions of years, and they will wait a little longer while you make yourself comfortable. Tonight, we travel far. We travel in the imagination and in the science across the full breadth of our galaxy, the Milky Way. A structure so enormous, so gently staggering in its dimensions, that the simple act of thinking about it carefully and thoroughly, with patience and sustained attention, is itself a kind of meditation. Our question this evening is a calm and thoughtful one, not a frightening one, not a sensational one, but simply this: what would it actually mean for a human being to attempt a crossing of the entire Milky Way galaxy from one edge to the other? And why is such a journey, in every meaningful physical and biological and engineering sense, something that lies gently beyond the reach of any human life as we currently understand it? This is not a question designed to unsettle you. It is a question designed to open something quietly remarkable in the mind, a subtle shift in perspective, a gentle recalibration of what we think we know about distance and time, and the fragile, beautiful smallness of a human body, placed against the backdrop of 100,000 light-years of spiraling starlight. Gently orbit the enormous, and still gently orbit the enormous and still somewhat mysterious center of our galaxy, and we will come to understand, in the calmest and most thorough way, why a creature made of carbon and water and delicate biological chemistry simply cannot, in any currently imaginable form, make this crossing and arrive intact on the other side. And in doing so, we will come to appreciate not the smallness of the human being before the universe, but the extraordinary, quietly remarkable fact that a creature as small and as brief as a human being can hold the entire galaxy in its mind, can measure it, can map it, can understand its structure and its history and its slow, majestic evolution across billions of years of cosmic time. So let us begin slowly, as all good journeys do, not at the destination, but at the very beginning, at the moment when human beings first began to understand what the Milky Way actually was, and how many hundreds of years of patient observation and careful reasoning it took for that understanding to gently evolve into the picture we now hold. On almost any clear night, in a place far enough from the glow of cities, you can look upward and see it. A soft band of faint light arching across the sky, diffuse and quiet, neither sharp nor dramatic, more like a watercolor stroke than a line drawn with precise intent. It is not bright enough to read by, not organized enough to mistake for a cloud, not focused enough to be a single object. It simply lies there, stretched from horizon to horizon in a long arc, patient and permanent, and very, very old. Ancient peoples around the world saw this band and gave it names and stories. The Greeks called it Galaxias Kyklos, the Milky Circle, and from that root word, gala, meaning milk, we eventually derived the word galaxy itself, a word that now describes not only this soft band of light overhead, but every vast island of stars scattered across the observable universe, from the nearest to the most distant ever detected. The Romans called it the Via Lactea, the Milky Way, and that name, translated into the languages of the modern world, has persisted through the millennia to the present day. The Egyptians saw it as a celestial river, a counterpart in the sky to the Nile stretching across the desert below. Indigenous peoples on every continent gave it their own names, their own meanings, their own place in the great narrative frameworks through which human beings have always tried to make sense of the cosmos they find themselves within. For the longest stretch of human history, however, no one knew precisely what this band was. It was beautiful and mysterious, and it was there, and that was, for a very long time, enough. The tools and conceptual frameworks needed to understand the Milky Way as a physical structure, as a collection of stars of a particular shape, extent, and organization, with the sun embedded within it at a specific location, were not available to the ancient world. The idea of stars as distant suns, of the sun as one ordinary member of a vast stellar family, of the galaxy as a physical object with a structure that could be measured and mapped. All of these ideas required not only better telescopes, but an entirely different framework for thinking about the universe and the place of the Earth and Sun within it. The understanding that the Milky Way was composed of individual stars, enormous numbers of stars, so densely packed along certain lines of sight that their combined light blurred into a continuous soft glow, came gradually and not all at once. Galileo Galilei, in the early 17th century, turned his newly improved telescope toward the Milky Way and discovered, with what must have been a quietly overwhelming sense of wonder, that the Milky Band was not a cloud or a vapor at all, but an ocean of individual points of light, stars beyond counting, all too faint and too distant to be resolved by the unaided eye into individual pinpoints. This was an early and important step. The Milky Way was stars. The stars were real, discrete objects, and there were many more of them than the naked eye could detect. But understanding the shape of the system those stars formed, its full extent, its structure and dynamics, and its relationship to the broader universe, that took much longer, and it required not just better telescopes, but a fundamentally new way of thinking about where in space the observer was located. For much of the 17th and 18th centuries, astronomers worked with the assumption that the sun sat somewhere near the center of the stellar system, and that the system itself had a somewhat flattened lens-like shape, extending farther in certain directions than others. This was not an unreasonable conclusion from the data available, because when you look at the Milky Way from within its disk, the concentration of stars along the band of the Milky Way appears roughly symmetrical around the observer, suggesting misleadingly that the observer is at or near the center. Thomas Wright, an English astronomer and instrument maker working in the mid-18th century, proposed in 1750 that the Milky Way might be a flattened layer of stars, a kind of grindstone or millstone shape, and that we were embedded within it, looking outward in all directions. He drew the basic picture correctly in its broad strokes. The Milky Way as a flattened disk of stars, even if he did not have the tools to determine its true extent or the position of the sun within it. Immanuel Kant, the philosopher, read about Wright's ideas and developed them in a remarkable direction, proposing that what we called the Milky Way was a gravitationally bound system of stars, what he called an island universe, and that the faint nebulae visible through telescopes might be other distant island universes of the same kind, far off across a space so enormous as to be nearly inconceivable to the minds of his contemporaries. Kant's leap from Wright's flattened disk model to the idea of multiple island universes was purely philosophical and speculative, not based on any observational evidence that he himself had gathered. But it was a leap of genuine intellectual courage and imagination, and it pointed in a direction that 2 centuries of subsequent astronomy would eventually confirm as broadly correct. Through the 18th and 19th centuries, astronomers like William Herschel and his son John Herschel made enormous systematic efforts to map the stars by counting them in different directions, a technique William Herschel called stargazing, trying to infer the shape of the galaxy from the distribution of stellar densities across the sky. Herschel spent decades at his telescope, systematically sweeping across different regions of the sky and recording how many stars were visible in each field of view, assuming that fainter stars were simply more distant and that the density of stars per unit volume of space was roughly constant throughout the stellar system. From these painstaking counts, he constructed a model of the galaxy as an irregularly shaped, somewhat flattened system of stars with the sun near its center. A model that was genuinely illuminating for its time, even though it was distorted by a systematic error whose nature would not be understood until more than a century later. That systematic error was interstellar dust. The space between the stars is not entirely empty. It contains, dispersed through the interstellar medium, a thin population of microscopic solid particles, dust grains composed of silicates and carbon compounds, whose cumulative effect on light passing through them is to absorb and scatter it, reducing the apparent brightness of distant stars and making them appear to be farther away than they actually are, or making very distant stars invisible altogether. The dust is concentrated primarily in the plane of the galactic disk, precisely the region where the density of stars is highest and where the structure of the galaxy is most interesting. This meant that Herschel's star counts in the plane of the Milky Way were not seeing to the true edge of the galaxy, but only to the effective horizon imposed by interstellar absorption. A horizon that happened to be roughly the same distance in most directions from the sun, creating the misleading impression that the sun was near the center of the stellar system. It was not until the early 20th century that the role of interstellar dust in obscuring distant stars was fully understood and properly incorporated into models of the galaxy's structure. And the correction of this systematic error was one of the keys to determining the sun's true position within the galaxy. The question of the sun's position within the Milky Way, whether we sat near the center or somewhere off to one side, was not properly answered until the early 20th century, and its resolution came from an unexpected direction. Harlow Shapley, an American astronomer working at the Mount Wilson Observatory in California, in the years around the First World War, turned his attention to the distribution of globular clusters, those ancient, densely packed spherical swarms of hundreds of thousands of stars that orbit the galaxy like satellites orbiting a planet, distributed in a roughly spherical halo around the galactic disk. Shapley recognized that globular clusters, being distributed above and below the plane of the disk rather than within it, would be affected much less by interstellar dust absorption than objects in the disk itself, and therefore their distances could be estimated more reliably using the available distance measurement techniques. Shapley used a class of pulsating stars called Cepheid variables, stars that vary regularly in brightness over periods of days to weeks, with a relationship between their period of pulsation and their intrinsic luminosity that made them reliable distance indicators to estimate the distances to the nearest globular clusters. He then used other methods to extend these distance estimates to the more distant clusters, building up a three-dimensional picture of the globular cluster system's distribution in space. What he found was immediately significant. The globular clusters were not evenly distributed across the sky. They were clustered much more densely in the direction of the constellation Sagittarius, piling up in that one quadrant of the sky with an asymmetry that told a clear and unmistakable story. If the Sun were near the center of the galaxy, the globular clusters, distributed in a roughly spherical halo centered on the galaxy's center, ought to appear more or less evenly distributed around it. The fact that they were concentrated strongly in the direction of Sagittarius meant that the center of the galaxy was not here, near the Sun, but over there, in the direction of Sagittarius, at a significant distance. Shapley's calculations placed the Sun roughly 30,000 light-years from the galactic center, a figure that subsequent refinements have revised to approximately 26,000 light-years. And he estimated the total diameter of the galaxy at approximately 300,000 light-years, a number that was later revised downward to the now accepted value of roughly 100,000 light-years, as the systematic errors in his distance calibrations were identified and corrected. Despite these overestimates in the absolute scale, the essential finding was correct and quietly revolutionary. The Sun was not at the center of the Milky Way. It sat in one of the galaxy's outer spiral arms, at a substantial distance from the center, rotating around the galactic core with a quiet, patient orbital velocity that carried it around the full circuit once every 225 million years or so. A period of time so long that it has its own quiet name, a cosmic year or a galactic year. In the entire history of the Earth, which formed roughly 4.5 billion years ago, the solar system has completed only about 20 such galactic orbits. Shapley's findings displaced the Sun, and with it, the Earth and every human being who had ever looked up at the night sky, from any central or privileged position in the galaxy. We were, as it turned out, occupants of an ordinary neighborhood in a large and otherwise unremarkable part of a spiral arm, about halfway between the center and the outer edge of a moderately sized galaxy. This was not, on reflection, a diminishing thought. It was a clarifying one, a quietly important step in the long process of understanding our actual location in the cosmos. It placed us in a specific position within a specific structure, and it made the universe feel, in a gentle and somewhat paradoxical way, more available to be understood, more fully inhabitable by the mind, even as it made it feel incomprehensibly larger than anything previous generations had imagined. At around the same time as Shapley was working out the position of the Sun within the galaxy, a parallel and deeply consequential debate was unfolding in the astronomical community about the nature of the spiral nebulae. Those faint, fuzzy patches of light, visible in telescopes, that seemed to have a spiral structure reminiscent of the Milky Way itself when viewed from an appropriate angle. Some of these nebulae, the Andromeda Nebula being the most prominent and the brightest, were visible to the naked eye in dark skies as faint smudges of light in the constellation Andromeda. And through a telescope, they revealed the characteristic sweep of a spiral pattern, two arms of faint light curving away from a bright central nucleus. Were these spiral nebulae simply clouds of gas and dust within the Milky Way, perhaps forming stars, perhaps remnants of older stellar systems? Or were they, as Kant had speculated nearly 2 centuries earlier, and as a growing number of astronomers in the early 20th century were seriously proposing, entire separate galaxies, island universes comparable to our own in size and stellar population, lying at enormous distances beyond the edge of the Milky Way? This was the great debate of early 20th century astronomy, and it was resolved with characteristic patience and the accumulation of better data by Edwin Hubble in the 1920s. Working at the Mount Wilson Observatory with the then largest telescope in the world, Hubble identified individual stars within the Andromeda Nebula, resolved individual stellar points from the blur of the spiral's outer regions, and recognized among them the characteristic light curves of Cepheid variable stars. Using the period luminosity relationship that had been calibrated on nearby Cepheids, whose distances were known, he calculated the distance to the Andromeda Nebula and found a number that placed it far, far beyond any conceivable boundary of the Milky Way, hundreds of thousands of light-years away, at a distance later revised and refined to approximately 2.5 million light-years. The Andromeda Nebula was not a nearby gas cloud. It was an entire galaxy in its own right, a system of stars comparable to the Milky Way in its great sweep and stellar population, lying at a distance that made even the enormous diameter of our own galaxy seem like a local measurement. Kant had been right more than 1.5 centuries before the observational confirmation arrived. In all directions toward a cosmic horizon. In all directions toward a cosmic horizon that Hubble and the generations of astronomers who followed him would spend the rest of the 20th century and beyond mapping and characterizing with increasing precision and care. The universe was not the Milky Way. The Milky Way was merely one component of the universe, one among hundreds of billions of galaxies distributed across the observable cosmos in a vast and intricate web of filaments, sheets, and clusters separated by enormous voids of near-empty space. What Hubble and Shapley and the long succession of careful observers before them had gradually revealed was a picture of extraordinary scale and quiet grandeur. A galaxy 100,000 light-years across, containing somewhere between 100 billion and 400 billion individual stars, with the Sun and its small family of planets situated in a comfortable and not particularly remarkable position within one of the galaxy's spiral arms, orbiting the center at a gentle and steady pace. And somewhere in that center, in the direction of Sagittarius, in the region Shapley had identified, using the globular clusters as his guide, lurked something enormous and compact, a central mass whose gravitational influence reached outward across thousands of light years, shepherding the orbits of stars that swooped around it in tight, high-speed ellipses, unlike the stately circular orbits of the disk stars farther out. That central mass, now known as Sagittarius A star or SGR A star, is generally described as a supermassive black hole with a mass estimated at about 4 million times the mass of the Sun, an object whose gravity is so concentrated that not even light can escape from within a certain radius around it. The existence of this object was suspected for decades before it was directly confirmed, inferred from the high-velocity orbits of stars moving around it. Orbits that could only be explained by the presence of an enormous concentration of mass in a very small region of space. In 2022, the Event Horizon Telescope collaboration, a network of radio telescopes distributed across the Earth and linked together through a technique called very long baseline interferometry to function as a single instrument nearly the size of our entire planet, produced an image of the region immediately surrounding Sagittarius A star, showing the characteristic ring of glowing gas and the dark central shadow that marks the boundary beyond which the black hole's gravity prevents any information from escaping. It was an image of extraordinary scientific significance, representing the culmination of decades of work by thousands of researchers, a century-long chain of theoretical prediction and observational effort, arriving at a single blurry but deeply meaningful picture. Though it is worth noting, in the spirit of the careful and open scientific process, that even this picture retains some gentle uncertainty at its edges. More recent research has proposed the intriguing possibility that the mass at the center of the Milky Way might not be a traditional supermassive black hole in the most straightforward sense, but rather an enormous, dense concentration of dark matter, the mysterious, invisible substance that accounts for most of the mass in the universe, but which has never been directly detected or fully characterized by any instrument. A dense enough clump of dark matter, the argument runs, could produce precisely the gravitational effects observed. The high-speed orbits of the S-stars racing around the galactic center, the bending of light, even the appearance of a shadow in radio, imaging that looks very much like the shadow of a black hole. This possibility has not replaced the black hole model, which remains the most straightforwardly consistent explanation with the evidence currently available. But it illustrates something gently important about the nature of scientific knowledge. Even our most carefully confirmed pictures of reality retain their edges of uncertainty, their open questions, their quiet invitations to keep looking and keep wondering, to hold our models with a kind of humble confidence rather than treating them as finished and complete. Now that we have arrived at a broad understanding of what the Milky Way is, a barred spiral galaxy, roughly 100,000 light-years in diameter and roughly 1,000 light-years thick in the disk region, with a central bulge of perhaps 10 to 12,000 light-years across, containing hundreds of billions of stars, orbited by ancient globular clusters, surrounded by a vast and diffuse halo of dark matter extending for hundreds of thousands of light-years in every direction. Now that we have this picture assembled in our minds, let us begin to gently inhabit the scale of it, to try to feel what these numbers actually mean, not as abstractions, but as something approaching a lived dimension of reality. A light year is the distance that light travels in 1 year, moving at approximately 300,000 kilometers per second, the fastest speed that anything in the universe can travel, according to our current understanding of physics. In 1 second, light travels far enough to circle the entire Earth approximately 7.5 times. In about 8 minutes and 20 seconds, it travels from the Sun to the Earth. In about 4.25 years, it travels from the Sun to the nearest other star system, the triple star system of Alpha Centauri, which lies at a distance of approximately 4.25 light years, close enough to be our nearest neighbor in the stellar community, but still so distant that the fastest spacecraft ever launched by human civilization would take tens of thousands of years to reach it. These are already large numbers by any human measure, but they are nothing, truly, gently nothing, compared to the scale of the galaxy. The distance from one edge of the Milky Way to the other is not 4 light years, not 40, not 400, but approximately 100,000 light years. If you were somehow traveling at the speed of light, which, as we will discuss at some length, is already far beyond anything a human-made spacecraft has ever approached or could approach with any foreseeable technology, it would still take you 100,000 years to cross our galaxy from rim to rim. 100,000 years of continuous travel at the maximum speed the universe allows, with no stops, no detours, no delays. Let us sit with that for a moment, very quietly, allowing the number to settle rather than rushing past it. The entirety of recorded human history, from the first clay tablets, the first pictographic writing, the first cities rising from river valleys in Mesopotamia and Egypt and the Indus Valley, the whole long, slow unfolding of civilization through agriculture and empire and philosophy and science and technology, spans roughly 5,000 to 6,000 years. The history of anatomically modern humans on Earth stretches back perhaps 300,000 years, to the time of our earliest identifiable ancestors walking across the landscapes of ancient Africa. The 100,000 light-year diameter of the Milky Way, expressed as a travel time even at the maximum speed the universe allows, is approximately equal to the entire span of anatomically modern human existence on this planet, from the very first human being to the very last one in our species' history so far, laid end to end in time. That is how long a light-speed journey across the Milky Way would take. And that is at the speed of light, which is not an engineering goal, but a fundamental physical limit, a ceiling that cannot be reached, only approached asymptotically. Our fastest spacecraft, the Voyager probes launched in 1977, and now drifting outward through the interstellar medium beyond the heliopause at the edge of the solar system, travel at roughly 17 kilometers per second relative to the Sun. An extraordinary speed by any terrestrial measure, fast enough to cross the continental United States in a matter of minutes. Fast enough to leave the solar system entirely over the course of a human lifetime, but a number that shrinks to a whisper when placed against the scale of interstellar distance. At Voyager's speed, reaching even the nearest star system would take approximately 70,000 years. Crossing the full 100,000 light-year diameter of the Milky Way at that speed would require something in the neighborhood of 2 billion years, a duration that substantially exceeds the current age of the Earth, which formed roughly 4.5 billion years ago. At 15 times Voyager's speed, a speed still utterly beyond any existing propulsion capability, the crossing would still require hundreds of millions of years. These are not engineering challenges waiting for a solution around the next corner. They are expressions of distance so vast that they gently reframe the question from one of technology to one of fundamental physical limits, and from one of engineering to one of cosmological scale. Now let us gently shift the frame, as scientists and thoughtful writers have both done, and ask what would happen if we could travel much, much faster than Voyager. If we could somehow approach a meaningful fraction of the speed of light. This is where the physics becomes quietly fascinating, and where the human body, that fragile and beautiful arrangement of chemistry and biology, begins to encounter the universe's more demanding requirements. The physics of traveling at speeds close to the speed of light are governed by Einstein's special theory of relativity, a framework whose development occupied the years between 1905 and 1916, and whose implications changed our understanding of space and time in ways that remain quietly astonishing more than a century later. One of the most gently counterintuitive consequences of special relativity is time dilation, the phenomenon by which a traveler moving at a very high speed experiences time passing more slowly than an observer at rest relative to the traveler. The closer you travel to the speed of light, the more pronounced this effect becomes, and above roughly 80% of the speed of light. The slowing of time becomes dramatic in ways that would have real consequences for a traveler who could somehow survive the journey and wished to return to the world they had left. The mathematics of time dilation are described by a simple formula involving the Lorentz factor, a number that equals 1 at rest and increases without bound as velocity approaches the speed of light. At 50% of the speed of light, the Lorentz factor is approximately 1.15, meaning that a traveler's clock runs about 15% slower than a stationary observer's clock. At 90% of light speed, the Lorentz factor rises to approximately 2.3, meaning the traveler ages only about half as fast as the stationary observer. At 99% of light speed, the factor reaches approximately 7. At 99.9%, it reaches about 22. At 99.99%, it climbs to roughly 70. These numbers mean that a traveler at very high fractions of light speed could, in principle, traverse the full 100,000 light-year diameter of the Milky Way in a subjective ship time of a few thousand years, even though 100,000 years would pass in the outside universe, or at even higher velocities in an even shorter subjective time. If a spacecraft could somehow achieve and sustain a continuous acceleration of approximately 1 gravity, the same gentle, familiar pull that presses you into your chair or your bed as you listen to these words tonight, then, over the course of months, it could build up to a substantial fraction of the speed of light, and over the course of approximately 1 year, it would reach 90% of light speed, and within a few years of sustained acceleration, it would achieve velocities very close to the speed of light, decelerating at 1 gravity for the second. Decelerating at 1 gravity for the second half of the journey to arrive at rest at the destination could cross the full diameter of the Milky Way in a subjective crew time of roughly 30 years or so, even though 100,000 years would pass on Earth during that journey. This is not a violation of physics. It is an exact, mathematically precise consequence of special relativity. but it produces a disorienting and quietly melancholy situation in which any travelers who somehow survived the journey and any hypothetical return journey would find the Earth transformed beyond recognition, its civilizations risen and fallen and replaced and fallen again many times over, its geological and biological landscape altered by the slow processes of tectonic movement and evolution and climate change, separated from the traveler's time of departure by a gulf of 100,000 years. But this thought experiment, quiet and elegant as it is, rests on an enormous and presently unreachable assumption that a spacecraft could somehow maintain a continuous acceleration of one gravity for years or decades on end. The energy requirements for such a journey are staggering in ways that defy easy analogy and that illuminate just how far beyond current human capability any approach to relativistic space travel lies. To accelerate a spacecraft of any reasonable mass to a significant fraction of the speed of light requires an amount of energy that exceeds anything remotely producible by human technology today, or in any near-term future that can be described with any credibility. A spacecraft carrying enough fuel to achieve even 10% of the speed of light, using conventional chemical or nuclear thermal propulsion, would need to carry a mass of propellant so enormous relative to the payload that the engineering becomes recursive in the most demanding way. More fuel to carry more fuel to carry more fuel, until the structural concept collapses under its own weight, and the mass ratio required makes the mission simply unachievable as conceived. This is what rocket engineers call the tyranny of the rocket equation. The exponential relationship between the mass ratio of fuel to payload and the velocity change achievable. A relationship that penalizes high-velocity missions with brutal efficiency. For a chemical rocket, achieving even a modest fraction of light speed would require a mass ratio of propellant to payload so astronomical as to be physically absurd. For nuclear thermal propulsion, the situation improves, but not nearly enough. For nuclear pulse propulsion, using successive nuclear detonations to drive the spacecraft forward, the situation improves further, with theoretically achievable velocities of perhaps a few percent of light speed. But the propellant mass requirements remain enormous, and the engineering challenges are substantial. The fundamental problem is that the energy required to accelerate a given mass to near light speed is immense, and carrying enough propellant to provide that energy adds to the mass that must be accelerated, which requires still more energy and more propellant in an escalating cycle. Various more exotic propulsion concepts have been proposed over the decades, and each represents a genuine and intellectually interesting area of scientific and engineering thought, worth exploring with calm attention, even if their realization lies in the distant future or remains deeply uncertain. The Bussard ramjet, proposed by physicist Robert Bussard in 1960, imagined a spacecraft equipped with an enormous electromagnetic scoop that would gather the thin hydrogen of the interstellar medium and feed it into a fusion reactor, using the abundant fuel of deep space itself rather than carrying propellant. The concept was elegant in its vision, a ship that grew faster as it traveled, continuously scooping fuel from the very environment it moved through. But subsequent analysis showed that the density of interstellar hydrogen in most of the galaxy is too low to sustain useful fusion in this way, and that the drag imposed by the electromagnetic scoop on the interstellar medium would likely exceed the thrust produced by the fusion reactions, making the ramjet scheme unworkable in the form originally imagined. Laser-driven light sails, thin, highly reflective sheets of material that could be accelerated by the pressure of photons from a powerful ground-based laser directed at the sail from a station near the spacecraft's departure point, requiring no onboard propellant and thus avoiding the recursive mass problem entirely, represent one of the more thoughtfully studied concepts for achieving significant fractions of light speed for small payloads. A sufficiently powerful laser directed at a sufficiently thin and reflective sail of sufficiently large area could, in principle, accelerate a sail to 20 or 30% of light speed over a period of minutes to hours. The breakthrough Starshot initiative, announced in 2016 and funded by a group of scientists and philanthropists, proposed exactly this concept for a mission to the nearest star. Tiny gram-scale spacecraft attached to meter-scale sails, accelerated by a gigawatt-scale laser array to approximately 20% of light speed, capable of reaching Alpha Centauri in roughly 20 years of flight time. Even this project, targeting the nearest star at a little over 4 light-years, rather than the full diameter of the galaxy at 100,000 light-years, represents an engineering challenge of enormous scale, and its practical realization, if it occurs at all, lies decades away at minimum. Scaling the concept to galactic distances would require propulsive power and infrastructure of a fundamentally different order, and the receiving end of the journey would offer no deceleration capability unless another laser installation existed at the destination, which rather presupposes the solution to the problem rather than contributing to it. Antimatter propulsion, using the mutual annihilation of matter and antimatter to generate the most energy-dense reaction physically possible, converting mass directly to energy with a theoretical efficiency of 100%, has been studied as a theoretical means of achieving high fractions of light speed. The annihilation of matter and antimatter produces gamma rays and other particles carrying energy equivalent to the full rest mass of both particles involved, providing vastly more energy per unit mass than any chemical or nuclear fission reaction, and considerably more than nuclear fusion as well. The physics of the energy release is impressive, and an ideal antimatter drive, if all of the annihilation energy could be captured and directed as thrust, would be capable of powering a spacecraft to relativistic velocities with a manageable mass ratio. The obstacle is entirely practical. Antimatter does not occur naturally in any significant quantity in the accessible environment around Earth, and producing it requires accelerating ordinary matter particles to high energy and inducing collisions that create matter-antimatter pairs, a process whose efficiency is extraordinarily low. The global production capacity of all particle accelerators currently in operation is measured in nanograms of antihydrogen per year, a quantity so small that it would take millions of years to accumulate the kilograms of antimatter that even a modest relativistic spacecraft would need. And storing antimatter safely in useful quantities requires magnetic confinement systems of a sophistication and scale that does not yet exist. These propulsion concepts, and the many others that have been proposed and studied to varying degrees of rigor over the decades, share a common character. They are genuine extrapolations of known or plausible physics, not violations of it, and they describe real, if distant, possibilities rather than pure fantasy. What they also share is an enormous gap between current capability and the capability needed. A gap that is not measured in years or decades, but in the slow unfolding of technological civilization across generations and perhaps centuries of future development. The gap between our current fastest spacecraft and the velocities needed for any meaningful galactic crossing is so large that the word gap feels almost inadequate for it. It is more like the distance between a candle and the sun, a difference not merely of degree, but of fundamental kind. So the energy and propulsion challenge alone places the crossing of the Milky Way gently but thoroughly beyond the reach of any technology we can currently envision or describe with any engineering specificity. But let us continue, because the physical and biological challenges of such a journey do not stop at propulsion. And understanding the full picture of why the crossing is so far beyond human reach requires exploring each of the other dimensions of the problem with the same patient attention we have given to the question of speed. Even if the energy and propulsion problem could somehow be set aside, even if we allow ourselves the thought experiment of a spacecraft capable of reaching a meaningful fraction of the speed of light, the human body, the actual living, breathing, thinking organism that would be making this journey, faces a set of challenges that accumulate with quiet relentlessness over the course of any sufficiently long voyage through deep space. These challenges have been studied with increasing rigor over the past several decades, driven in large part by the practical urgency of planning longer human space missions. First to the Moon, now with serious attention toward Mars, and in more speculative contexts toward farther destinations. And the picture they paint is one of a biological system gently but consistently pushed beyond the conditions for which it evolved. The first, and perhaps most thoroughly studied of these challenges, is radiation. Specifically, the radiation environment of deep space beyond the protective embrace of Earth's magnetic field. Here on the surface of the Earth, we are gently wrapped in a double layer of protection that most of us never think about, and whose absence we would notice almost immediately. The Earth's magnetic field, generated by the churning of liquid iron in the planet's outer core and extending outward for tens of thousands of kilometers above the surface, deflects the vast majority of charged particles streaming outward from the Sun and from deep space, shepherding them around the planet in graceful arcs along magnetic field lines, rather than allowing them to rain down unimpeded on the surface below. The atmosphere provides a second layer of protection, absorbing and scattering most of the radiation that does manage to penetrate the magnetic shield and ensuring that the radiation reaching any living organism at sea level is a small fraction of what exists even at the top of the atmosphere, let alone in open space. Step beyond these protections, as astronauts must when they travel above low Earth orbit, and the radiation environment changes in ways that are quietly significant. Two main categories of space radiation are relevant here, and they are quite different in their character and their implications for shielding and biological protection. The first is solar energetic particles, bursts of high-energy protons and other charged particles ejected by the Sun during solar flares and coronal mass ejections, events that occur with varying frequency depending on the phase of the 11-year solar activity cycle. These solar particle events can deliver large doses of radiation over periods of hours to days and represent a genuine acute hazard for unprotected astronauts in deep space. They are, however, somewhat manageable. Solar activity can be monitored with advance warning of hours to days in some cases, and a spacecraft can carry a dedicated storm shelter of dense shielding material into which crew members can retreat during particularly energetic events. Solar particle events are intense but episodic, and the biological dose delivered depends strongly on the specific event and the quality of shielding available. The second category, galactic cosmic rays, is in many ways the more persistent and biologically consequential challenge for long-duration deep space travel. Galactic cosmic rays are high-energy particles, primarily protons and helium nuclei, with smaller contributions from the nuclei of heavier elements including iron, that have been accelerated to near light speed by the most energetic astrophysical processes in the galaxy. The shock fronts of expanding supernova remnants, the energetic environments near neutron stars and other compact stellar remnants, the active regions of galactic nuclei. These particles arrive from all directions with a relatively uniform flux, continuously and without pause, and they carry enough energy to penetrate significant thicknesses of material, including the walls of a spacecraft and the tissues of a human body. Unlike solar particle events, which can be partially reduced by shielding, the most energetic galactic cosmic ray particles pose a more complex challenge. Adding more shielding material can, in some situations, make the problem worse, because the cosmic ray particles interact with the nuclei in the shielding material and produce secondary showers of radiation. Lighter particles, gamma rays, neutrons, that can in some cases deliver a higher biological dose than the original primary particles would have. When a high-energy cosmic ray particle passes through a living cell, it deposits energy along its path through a process called ionization, stripping electrons from atoms and molecules and creating reactive charge species and free radicals that interact with and damage the molecular machinery of the cell. The most consequential form of this damage is to DNA, the long double-stranded polymer molecule that carries the genetic instructions of every cell in the body, containing in its sequence the information needed to build and maintain every protein and structure and process that constitutes a living organism. Galactic cosmic rays, particularly the heavy high-energy nuclei called HZE particles, high atomic number, high energy, are especially effective at producing complex clustered DNA damage. Multiple breaks and lesions concentrated in a small region of the DNA molecule, which the cell's repair mechanisms find much more difficult to address correctly than the simpler single-strand breaks that most ordinary radiation sources produce. The cell has sophisticated repair mechanisms for DNA damage, enzymes that patrol the genome continuously, detect damage, and work to correct it with remarkable accuracy. These mechanisms evolved over billions of years of life on Earth, dealing with the DNA damage caused by natural background radiation, ultraviolet light, and the reactive oxygen species produced as byproducts of normal cellular metabolism. They are genuinely impressive biological machines, capable of detecting and repairing thousands of DNA lesions per cell per day with high fidelity. But they have limits, and the complex clustered damage produced by HZE cosmic ray particles strains those limits significantly. When complex damage is not repaired correctly, when the two ends of a broken DNA strand are rejoined incorrectly, or when a damaged template is copied in a way that introduces an error, the result is a mutation, a permanent change in the sequence of the genome that can, if it occurs in a gene or regulatory region with important functions, alter or disable those functions in ways that range from silent and irrelevant to significantly harmful. The accumulation of such mutations over time, particularly in cells that divide frequently and whose accurate replication is important for tissue maintenance, is associated with increased rates of cancer. The class of diseases characterized by the uncontrolled proliferation of cells, whose growth control mechanisms have been disrupted by accumulated genetic damage. The risk of radiation-induced cancer for astronauts on long-duration deep space missions is one of the most carefully studied aspects of space medicine, and the estimates, while uncertain in their precise values, consistently suggest that the radiation dose received on a mission of even moderate duration in deep space would meaningfully elevate lifetime cancer risk above baseline levels. Current NASA career radiation exposure limits for astronauts are set with the goal of keeping the increased lifetime risk of cancer mortality below 3%. A number that, while not trivial, is considered an acceptable occupational risk for the relatively short missions currently planned. A mission of years or decades in deep space would approach or exceed these limits many times over, and a mission lasting centuries or millennia would deliver doses orders of magnitude beyond any biologically manageable level without extremely effective shielding. The human nervous system appears to be particularly sensitive to the effects of high-energy heavy ion radiation. Neurons, the cells that form the brain and the broader nervous system, are largely non-dividing cells in adulthood, meaning that when they are damaged or killed, the body's capacity for replacement is quite limited, especially in critical regions like the hippocampus, which is important for learning and memory, and the prefrontal cortex, which is important for complex decision-making and behavioral regulation. High LET radiation, high linear energy transfer radiation, the category that includes the heavy nuclei of galactic cosmic rays, can damage the dendritic structures of neurons, the branching extensions through which neurons connect with and communicate with each other, in ways that may impair cognitive function, memory formation, and behavioral flexibility over time. Research conducted with animal models, primarily mice exposed to beams of heavy ions at particle accelerators, in doses and energies chosen to simulate the cosmic ray environment of deep space, has shown a consistent pattern of neurological and behavioral effects, including impaired performance on spatial memory tasks, increased expression of anxiety-like behaviors, reduced cognitive flexibility in tasks requiring adaptation to changing rules, and structural changes in neurons of the hippocampus and prefrontal cortex. These effects are not dramatic collapses of neurological function. The animals remain alive and capable of basic behaviors, but they represent a slow, subtle erosion of the more complex cognitive and emotional functions that depend on the integrity of specific neural circuits. For human beings, these circuits support not only memory and learning, but the kind of complex, adaptive, creative thinking that long-duration mission crew members would need to maintain at high levels for the entire duration of a journey. Beyond radiation, the second great biological challenge of long-duration space travel is the sustained weightlessness of free fall that spacecraft experience when they are not under acceleration. The human body evolved over hundreds of millions of years of evolutionary history in a constant, reliable gravitational field of approximately 9.8 meters per second squared, and virtually every major organ system has been shaped by the continuous gentle presence of this force. The skeletal system exists in its current form because it needs to support the body's weight against gravity, distributing mechanical stress through bones in patterns that stimulate the deposition of new bone mineral and the maintenance of bone density. The cardiovascular system pumps blood in the way it does, partly because it must push blood upward from the lower body against the downward pull of gravity, maintaining adequate blood pressure in the brain and upper body against a persistent hydrostatic gradient. The vestibular system, the intricate sensory apparatus of the inner ear, detects the direction and magnitude of gravitational pull and provides the brain with a constant reference frame for orientation and balance. The postural muscles of the back, abdomen, and legs are in a continuous state of low-level activation in normal gravity, maintaining posture and supporting movement against the gravitational load. Remove gravity from the equation, as spaceflight does, and all of these systems begin to slowly and quietly drift away from their evolved configurations. In the microgravity environment of a spacecraft in free fall, bone density decreases at a rate of approximately 1 to 2% per month in the most affected regions. A rate that, over the course of a 6-month mission, produces bone loss comparable in magnitude to the bone loss associated with years of postmenopausal osteoporosis in high-risk individuals. The weight-bearing bones of the skeleton, the lumbar vertebrae, the hip bones, the femur, are particularly affected, losing mineral density and structural integrity in ways that increase the risk of fracture both during the mission and upon any eventual return to a gravitational environment. The bone loss is not uniform, but concentrated in the most mechanically loaded regions in normal gravity, reflecting the fact that bone tissue is a dynamic, responsive material that remodels itself continuously in response to the mechanical forces it experiences, and that in the absence of those forces, the biological signals that promote bone formation are reduced, while those that promote bone resorption remain active. Muscle mass decreases in parallel with bone density, particularly in the postural muscles and the muscles of the legs and lower body that experience the most dramatic reduction in load in weightlessness. Studies of astronauts on the International Space Station have found reductions of 5 to 10% in the volume of key lumbopelvic muscles over the course of a 6-month mission, even with daily exercise countermeasures, with individual muscles showing losses at the higher end of this range. The muscles of the legs, the quadriceps, the hamstrings, the calf muscles show the most pronounced atrophy, with reductions in muscle fiber diameter measurable even over the course of a single week in microgravity. The consequences of this muscle loss would be felt immediately upon any return to a gravitational environment. Reduced strength, impaired coordination and balance, increased risk of falls and injuries during the period of readaptation. The cardiovascular system adapts to weightlessness in ways that are, in the short term, a reasonable response to the changed mechanical environment, but that create problems over longer durations. Without gravity pulling blood downward into the lower body, fluid shifts upward toward the head and chest, causing the heart and the baroreceptors, the pressure sensors in the blood vessels, to sense a higher blood volume in the thoracic region than is normal in gravity. The body interprets this as a state of relative fluid overload and responds by reducing total blood volume, excreting fluid through the kidneys, and reducing red blood cell production. This adjustment makes physiological sense in weightlessness, where the cardiovascular system does not need to push blood against a hydrostatic gradient, but it creates immediate difficulties if the traveler returns to a normal gravitational environment, where the reduced blood volume can be insufficient to maintain adequate perfusion of the brain upon standing, causing lightheadedness, fainting, and cardiovascular strain. Over longer durations, the heart itself may undergo structural changes, the cardiac muscle becoming somewhat less efficient as a pump, the left ventricle changing shape slightly in response to the reduced workload that prolonged weightlessness imposes. The visual system, too, appears to be affected by long-duration spaceflight in ways that researchers have only begun to characterize in detail over the past decade or two. A significant and growing proportion of astronauts who spend extended periods in space, particularly those on missions of 6 months or longer, develop a condition called spaceflight-associated neuroocular syndrome, or SANS, characterized by a constellation of findings including flattening of the posterior globe of the eye, swelling and congestion of the optic nerve head, the development of small patches of retinal damage called cotton wool spots, and shifts in visual acuity and refractive error that can persist for months or years after returning to Earth. The leading hypothesis for this condition involves the redistribution of cerebrospinal fluid in weightlessness. Without gravity pulling cerebrospinal fluid downward as it does on Earth, fluid pressure in the cranial cavity increases slightly compared to what the eye's internal pressure is adapted to resist. And this chronic, mild imbalance of pressures across the back of the eye is thought to mechanically deform the eye's posterior structures over time, pushing outward on the optic nerve and the scleral tissues in ways that produce the observed changes. For a journey lasting years or decades in microgravity, the cumulative effect on visual function would be significant. And for a journey lasting centuries or millennia, the question becomes not one of degree, but of fundamental viability. The immune system, the body's distributed network of cells, tissues, and biochemical signals that detect and respond to pathogens, cellular damage, and the constant low-level threat of mutant cells that might give rise to cancer, also behaves differently in the microgravity environment of space. Studies of blood samples collected from astronauts before, during, and after space missions have found changes in the populations of immune cells in circulation, alterations in the patterns of cytokine, signaling through which immune cells communicate and coordinate their responses, and reduced effectiveness of specific immune functions, including the killing of virus-infected cells and the response to vaccination. The mechanisms behind these immune changes are not yet fully understood, but they likely involve a combination of several contributing factors. The direct effects of radiation on immune cells, which divide rapidly and are therefore particularly sensitive to radiation-induced DNA damage. The effects of microgravity on the physical movement and interaction of immune cells, and the effects of the chronic, low-grade psychological stress of isolation and confinement on the hormonal and neurological signals that regulate immune function. Taken together, these biological challenges, radiation damage to DNA and neural tissue, bone and muscle loss, cardiovascular deconditioning, visual and intracranial pressure changes, immune suppression, form a picture of quiet but persistent pressure on the human organism. They are not dramatic or instantaneous failures. not the kind of sudden catastrophes that cinematic depictions of space hazards tend to favor. They are, instead, slow accumulations, gradual drifts, the patient wearing away of biological systems designed for a specific environment when placed in a very different one. Over sufficiently long durations, these individually manageable challenges interact with each other and compound, each one making the others slightly harder to bear, each one reducing the body's capacity to withstand and recover from the next insult, until the cumulative burden exceeds the capacity for recovery and repair. Exercise is the most effective countermeasure currently available for the muscle and bone losses of microgravity, and astronauts aboard the International Space Station spend approximately 2 hours per day on resistive and aerobic exercise equipment specifically designed to work the muscles and load the bones in the absence of gravitational loading. This regimen is remarkably effective. It substantially reduces, but does not entirely eliminate, the bone and muscle losses that occur in microgravity, and it allows astronauts to return from 6-month missions in a condition from which they can recover full physical function over a period of weeks to months. But the exercise countermeasure requires functional equipment, requires the time and energy of the crew, and does not address the radiation, the visual changes, or the immune alterations. And for a journey lasting decades or centuries rather than months, the question of how effective any exercise regimen could remain over such timescales in an aging population with accumulating radiation damage to tissues and organs is one whose answer is deeply uncertain. Nutrition and pharmacological countermeasures are also areas of active research. Certain antioxidants and other compounds have shown some ability to reduce radiation-induced cellular damage in laboratory models, and drugs targeting bone resorption pathways, already used on Earth to treat osteoporosis, have shown some benefit in reducing bone loss in space. Dietary optimization, including adequate calcium, vitamin D, and other micronutrients important for bone health, is part of standard space nutrition planning. But all of these countermeasures address the symptoms rather than the fundamental cause, which is the mismatch between the environment in which the human body evolved and the environment in which space travel takes place. Artificial gravity, achieved by rotating a spacecraft or part of a spacecraft to create centrifugal force that mimics the effect of gravity on the crew, is frequently discussed as a more fundamental solution to the microgravity problem, and it is physically plausible in principle. A rotating habitat of sufficient radius, spinning at the right rate, would create a centrifugal acceleration equivalent to Earth's gravity at the outer rim, providing the mechanical loading that bones and muscles and the cardiovascular system need to maintain their normal function. The engineering challenges of building and operating a large rotating spacecraft habitat are substantial, but not in principle fundamentally insurmountable. They are a matter of scale and structural complexity rather than of physics. But artificial gravity does not address the radiation problem, which is determined by the external radiation environment rather than by the gravity inside the spacecraft. And it does not address the psychological and social challenges of long-duration isolation. It would be a meaningful improvement on current space habitation conditions, but it would be one contribution to a solution rather than a complete solution in itself. Now, let us turn our attention from the body to the physical environment of the journey itself, because the Milky Way is not an empty place, and the path across it is not a smooth or featureless plain. The galaxy is filled in its interstellar spaces with a variety of materials and phenomena, tenuous but not absent, that a traveling spacecraft would encounter throughout its crossing. And understanding the nature of this interstellar medium helps us appreciate why the galaxy, for all its apparent emptiness, is a genuinely complex and varied environment through which any form of travel would need to navigate with care. The interstellar medium, the matter that fills the space between the stars, is composed primarily of hydrogen and helium gas, with smaller amounts of heavier elements and a dispersed population of microscopic solid particles known as interstellar dust. On the whole, the interstellar medium is extraordinarily thin by any everyday standard. The average density of the diffuse interstellar medium in the solar neighborhood is something like 1 hydrogen atom per cubic centimeter, a density so low as to be essentially indistinguishable from the best vacuum achievable in Earth laboratories. For comparison, the air you breathe at sea level contains approximately 27 million trillion molecules per cubic centimeter, a difference of roughly 19 orders of magnitude. In the spaces between stars, there is, for most practical purposes, nothing. But that near nothing is not entirely nothing, and at the speeds that would be necessary for any kind of practical galactic crossing, even the thin interstellar medium becomes a consideration worth thinking through carefully. A spacecraft traveling at 10% of the speed of light, a velocity that remains orders of magnitude beyond current capability, but is at least conceptually within the range of theoretical future propulsion schemes, would experience the individual hydrogen atoms of the interstellar medium not as a gentle ambient bath, but as a continuous stream of energetic particle impacts. At that speed, each hydrogen atom encountered by the spacecraft's forward surface would carry a kinetic energy in the spacecraft's reference frame, comparable to a moderately energetic cosmic ray particle. And the cumulative effect of billions of such impacts per second on the spacecraft's leading surfaces would cause gradual erosion and heating that would need to be accounted for in any engineering design. The structure of the interstellar medium is not uniform. It exists in a range of distinct phases with very different temperatures, densities, and compositions, determined by the balance of heating and cooling processes operating in different environments throughout the galaxy. The hot ionized medium, plasma heated to temperatures of 1,000,000 degrees or more by the shock waves of supernova explosions, fills perhaps 30 to 50% of the total volume of the galactic disk with a gas so diffuse that its total column of material is still quite small, but whose extreme temperature means that any object passing through it would absorb significant heat. The warm, neutral medium, hydrogen gas at temperatures of a few thousand degrees, denser than the hot phase but cooler and largely neutral, fills much of the remaining volume of the disk. Cold, neutral clouds, concentrations of hydrogen gas at temperatures of around 100 degrees Kelvin, dense enough to absorb radio waves at the characteristic 21 centimeter wavelength of neutral hydrogen, are distributed throughout the disk in clumps and sheets of varying size and density. And the cold, dark molecular clouds, the densest and coldest phase of the interstellar medium, with temperatures of only 10 to 30 degrees above absolute zero, and densities of hundreds to millions of hydrogen molecules per cubic centimeter, are the sites of active star formation, concentrated primarily along the spiral arms and representing the birthplaces of new generations of stars and planetary systems. A crossing of the galaxy would pass through all of these phases in varying proportions, the mixture changing as the path moved through different regions of the disk. Through the active star-forming spiral arms, where the interstellar medium is richest and most structured, through the quieter inter-arm regions where the gas is more diffuse and the stellar population older and less active, through the inner galaxy where the density of both stars and interstellar material increases toward the concentrated central bulge. In the densest molecular cloud regions, the column density of material along the path would be high enough to cause significant attenuation of any electromagnetic communication signal and to pose more significant erosion challenges for a high-speed spacecraft. Navigation through the galaxy would therefore involve not just pointing the spacecraft in the direction of the destination, but threading a path through the complex and inhomogeneous structure of the interstellar medium, avoiding the densest obstacles and choosing routes that balanced directness with navigability. The spiral arms of the Milky Way are among the most structurally interesting and visually distinctive regions of the galaxy, and a galactic crossing that passed through them would encounter environments qualitatively different from the quieter inter-arm regions. The Milky Way is classified as a barred spiral galaxy, meaning it has a central bar-shaped structure of stars and gas oriented across the galactic center, from which spiral arms emerge and wind outward through the disk. Current understanding identifies several major spiral arm features: the Perseus arm, the Sagittarius Carina arm, the Crux Scutum arm, and others, as well as minor arm features like the Orion spur in which the Sun currently resides. These arms are regions of enhanced density in the disk, concentrations of gas, dust, and young stars that represent a density wave pattern propagating through the rotating disk, analogous in some ways to a wave pattern in a fluid medium, where the wave itself is not made of fixed material, but rather represents a region where the material temporarily piles up and slows before moving on. The spiral arms are traced in the sky by the concentration of young, hot, brilliant blue-white stars, the most massive stellar objects, which burn through their nuclear fuel with extraordinary speed and spend their short but luminous lives near the regions of dense gas and dust where they were born, before exhausting their fuel and exploding as supernovae after only a few million years. This concentration of massive stars makes the spiral arms the brightest regions of the galaxy when viewed in blue and ultraviolet light, and the ongoing star formation within the arms fills them with HII regions, glowing clouds of ionized hydrogen lit from within by the ultraviolet radiation of newly born hot stars, shining in characteristic pinks and reds, and with the dark, pillar-like structures of cold molecular clouds whose outer surfaces are being slowly sculpted and eroded by the energetic radiation streaming from nearby stellar nurseries. Moving through a spiral arm, a hypothetical traveler would be surrounded by an environment notably richer in ionizing radiation than the quieter inter-arm regions, with the combined ultraviolet output of thousands of young hot stars contributing to an elevated radiation background on top of the ever-present galactic cosmic ray flux. Supernova remnants, the expanding shells of gas and magnetic field energy thrown outward by the deaths of massive stars, would be encountered with greater frequency in the arms than in the inter-arm spaces. Their ghostly filaments of glowing plasma and their compressed magnetic field boundaries representing both a visual spectacle and a source of energetic particle acceleration. The spiral arms are, in a gentle sense, the most alive regions of the galaxy. The places where matter cycles most actively between the interstellar medium and stellar objects. Where new suns are born and old massive ones die, where the chemical enrichment of the galaxy's gas reservoir is proceeding most rapidly through the contribution of heavy elements forged in stellar interiors and dispersed by supernova explosions. Between the spiral arms, the environment is quieter and in some ways more representative of the average character of the galactic disk. The inter-arm regions contain an older population of stars, the low-mass, long-lived stars that have been orbiting the galaxy for billions of years, drifting slowly away from the arms where they were born as they continue their orbital circuits, and as the spiral pattern shifts its phase relative to individual stellar orbits. The interstellar medium in inter-arm regions is thinner and more uniform, the rate of star formation lower, the density of giant molecular clouds reduced. It is a calmer landscape in the astronomical sense, slower in its evolution, quieter in its energy output, more settled in its long-term character. Continuing inward from the inter-arm regions toward the galactic center, the density of stars increases steadily and then sharply as the traveler moves from the thin disk into the thick disk and then into the central bulge. The thick disk is a component of the galaxy distinct from the thin disk in which the Sun resides. It extends farther above and below the plane of the galactic midplane, contains an older stellar population with a different chemical composition, and represents an earlier phase of the galaxy's formation history when the disk was geometrically thicker and less settled in its dynamics. Stars of the thick disk are on average older, more chemically primitive in the sense of containing lower abundances of heavy elements, and distributed in a puffier, less flattened distribution than the young blue stars of the thin disk. The central bulge, the roughly ellipsoidal concentration of mostly older, redder stars that swells upward and outward from the galactic center, presents a qualitatively different environment. The stars here are densely packed by the standards of the disk, their distances from their nearest neighbors smaller, their collective gravitational interactions more complex. Many of the stars in the bulge are ancient, formed in the earliest epochs of the galaxy's history, more than 10 billion years ago, when the first generations of stars were burning brightly and seeding the interstellar medium with the first significant quantities of elements heavier than hydrogen and helium. These stars carry in their chemical compositions a record of the galaxy's early history, their spectra revealing the abundance patterns of elements produced by the specific mix of stellar processes operating in the young galaxy before the many subsequent stellar generations had added their contributions to the chemical inventory of the interstellar medium. The central molecular zone, the innermost few hundred light-years of the galaxy immediately surrounding the galactic center, contains a large and complex reservoir of dense molecular gas, threaded by strong magnetic fields and heated by the intense radiation environment of this crowded inner region. Star formation in the central molecular zone is vigorous, producing young, massive star clusters that add their energetic output, ultraviolet radiation, stellar winds, eventually supernova explosions, to an already energetically rich environment. The interaction of these stellar energy sources with the dense surrounding gas produces complex hydrodynamic structures, shocks, bubbles, outflows, that are visible in observations across a wide range of wavelengths, from radio to X-ray, painting a picture of ongoing, energetically dynamic processes in the innermost regions of the galaxy. And then, at the very center, there is the compact mass itself. Sagittarius A star, the 4 million solar mass object whose gravity dominates the dynamics of the inner parsec of the galaxy, around which a small number of stars, known as the S stars, orbit in tight, high-speed ellipses that have been tracked and measured with extraordinary precision over the past 2 decades, yielding the most direct evidence for the mass and compactness of the central object. The innermost of these stars, S2, completes a full orbit around the galactic center in approximately 16 years, approaching within a few light hours at its closest point and moving at speeds of nearly 3% of the speed of light at periapsis. A speed so extraordinary for an object as large as a star that it leaves no room for doubt about the enormous mass concentrated in the tiny region the star swings around. The region immediately surrounding the central mass, within the event horizon radius of a few tens of millions of kilometers, is, in the framework of general relativity, a place of extraordinary curvature of space-time, where the geometry of space and the flow of time are distorted in ways that become dramatic in the immediate vicinity of the horizon itself. Far outside the horizon, the gravitational effects of Sagittarius A star are simply those of an unusually massive object, no different in principle from the gravitational influence of any other concentration of mass, affecting the orbits of nearby stars and gas clouds in ways that are complex but entirely calculable using well-tested gravitational physics. But closer in, as the tidal forces of the black hole's gravity become significant over distances comparable to the size of objects falling toward it, the environment becomes increasingly inhospitable to any extended material structure. Objects approaching the black hole within what is called the tidal disruption radius are subjected to differential gravitational forces, stronger gravity on the side facing the black hole, weaker on the far side, that exceed the structural strength of the object and tear it apart, spreading its material into a thin stream that spirals inward and is eventually swallowed. For a hypothetical spacecraft traversing the inner galaxy, the central black hole would not present a navigational hazard at any great distance. Its gravitational influence, while enormous in absolute terms, falls off with distance in the same inverse square fashion as any other gravitational source, and at distances of light years or more, it would simply be a gravitational attractor to be accounted for in trajectory planning, rather than an immediate danger. But the energetic environment of the central region, the concentrated radiation from dense stellar populations, the hot, diffuse plasma filling the inner few hundred light years, the complex magnetic field structures threaded through the central molecular zone, the occasional energetic outbursts from the central mass when it consumes a cloud of gas or the disrupted remnant of a star, would all contribute to a radiation environment significantly more intense than the typical disk environment, adding to the already considerable radiation burden of any crew making the crossing. After passing through the galactic center region, the journey would continue outward on the far side of the galaxy, through a mirror arrangement of the environments already traversed. Inner spiral arms gradually giving way to the quieter mid-disk regions, then the outer arms, then the thinning outer disk, and finally the gradual fade into the extragalactic void where the galaxy's edge blurs into the sparse and ancient stellar streams of the outer halo. The total path from edge to edge across the disk would span approximately 100,000 light-years, with every light-year of that path presenting its own specific combination of radiation environment, interstellar medium density, gravitational influences, and navigational considerations. The outer regions of the galactic disk, beyond the Sun's orbit, are in some ways the least well-characterized parts of the galaxy, partly because of the difficulty of measuring distances accurately to objects in the outer disk, and partly because the outer disk has traditionally attracted less observational attention than the more dramatic inner regions. But recent surveys of the outer Milky Way have revealed it to be a surprisingly rich and complex environment, with evidence of warping of the disk plane, a gentle bending of the disk out of its mean plane, likely caused by the gravitational influence of satellite galaxies orbiting the Milky Way. And with stellar populations and star formation activity extending to significantly larger radii than had previously been appreciated. The outer disk may also contain a higher proportion of pristine, chemically primitive gas than the inner disk, representing material that has not yet been processed through many generations of star formation and may retain something closer to the original chemical composition of the protogalactic cloud from which the Milky Way formed. Beyond the stellar disk, as we have mentioned, the dark matter halo extends for hundreds of thousands of light-years in every direction, an invisible scaffold of gravitational influence within which the visible galaxy is embedded. But the halo also contains the visible remnants of ancient gravitational interactions, the stellar streams that mark the disrupted cores of dwarf galaxies and globular clusters that have been captured and gradually torn apart by the Milky Way's tidal forces over billions of years of dynamical history. These streams, thin ribbons of stars stretched along the orbital paths of their former parent objects, crisscross the halo in complex patterns, their stars moving coherently in phase space even as they are spread across enormous distances in physical space. They are a kind of gravitational archaeology, encoding in their structure the history of interactions between the Milky Way and its smaller neighbors, a history that has been gradually revealed by the precise astrometric measurements of space missions like the European Space Agency's Gaia Observatory, which has measured the positions and motions of more than 1 billion individual stars with unprecedented precision. The Magellanic Clouds, the Large Magellanic Cloud and the Small Magellanic Cloud, the two most prominent satellite galaxies of the Milky Way, are visible from the southern hemisphere as bright, irregular patches of light in the night sky, lying at distances of approximately 160,000 and 200,000 light-years respectively. They are currently in the process of a gravitational interaction with the Milky Way that will eventually, over timescales of billions of years, result in their assimilation into the larger galaxy. A slow, gentle collision that has already produced a visible bridge of gas and stars stretching between the two clouds and the Milky Way, and that is gradually stripping material from the clouds and depositing it in the Milky Way's halo. These satellite galaxies represent a reminder that the Milky Way is not an isolated island universe, but a gravitationally dominant member of a local group of galaxies, interacting with its neighbors in ways that slowly but continuously shape its structure and evolution. The local group itself, The modest cluster of galaxies, of which the Milky Way and Andromeda are the two dominant members, contains perhaps 60 to 80 galaxies of various sizes, most of them small dwarf galaxies orbiting one or the other of the two large spirals. The local group occupies a region of space roughly 10 million light-years across, embedded within the larger Virgo supercluster and the still larger Laniakea supercluster, an enormous, loosely bound structure of galaxies and galaxy clusters identified in 2014, spanning approximately 500 million light-years and containing perhaps 100,000 galaxies within its gravitational influence. The Milky Way's 100,000 light-year diameter, vast as it is on any human scale, is only 1/5000th of the diameter of the Laniakea supercluster, and the observable universe, the portion of the universe from which light has had time to reach us since the Big Bang, extends for approximately 93 billion light-years, containing perhaps 2 trillion galaxies scattered through its volume. These numbers continue to gently expand the sense of scale, layer by layer, like opening a series of nested containers, each larger than the last, until the mind arrives at a horizon beyond which even the imagination grows quiet and still. Not from alarm, but from a kind of calm saturation, a gentle recognition that the universe is larger by a very great deal than anything that can be held in a single mental image. The Milky Way, which is itself so vast as to be effectively uncrossable by any human technology imaginable for the foreseeable future, is in the context of the broader universe a relatively small and ordinary structure, one modest spiral among uncountable billions, each with its own hundreds of billions of stars, each rotating slowly around its own central mass, each embedded in its own dark matter halo, each carrying within it the possibility of planetary systems and the slow, patient chemistry that might, in some small fraction of cases, lead to the emergence of life. Now let us return one more time to the human dimension of all of this, to the question of what it would mean, not physically or astronomically, but psychologically and socially, for human beings to undertake a journey of galactic scale. We have explored the physics and the biology, and we have found in each dimension a set of challenges that accumulates quietly but persistently to something gently beyond current capability. But there is another layer of the story that deserves careful and patient attention, because any serious attempt to think through the challenges of galactic travel eventually arrives at questions not of engineering or biology, but of human meaning, of what it would be like, from the inside, to be the person or the community making such a journey, and of whether the human spirit, as well as the human body, is suited to the demands that such a journey would place on it. The closest analogies we have from human experience are the long sea voyages of exploration, the crossings of the Pacific by Polynesian navigators, the circumnavigations of the globe by the great European maritime expeditions of the 15th and 16th centuries, the voyages into the unknown Arctic and Antarctic by the explorers of the 19th and early 20th centuries. These journeys shared certain features with the hypothetical galactic crossing. They involved traveling into environments that were hostile to human survival, with limited resources and no possibility of immediate rescue or resupply, in small groups of people who had to maintain functional social and operational cohesion over extended periods of time under significant stress. They also involved moving into regions of the world that were genuinely unknown, where the navigators had no reliable maps, no prior information about what they would encounter, and no certainty that they would find what they were looking for or return safely. But even the most extended of these terrestrial voyages lasted years at most, not centuries or millennia. The Antarctic expeditions of the early 20th century, among the most psychologically demanding of historical human journeys in terms of isolation, confinement, physical hardship, and uncertainty, lasted 1 to 3 years in their longest forms. The psychological research conducted on the communities that spend winter seasons at Antarctic stations, the most sustained modern analogue to long-duration space missions, has identified a characteristic pattern of psychological adaptation over the course of a winter overseason. An initial period of adjustment and orientation, a middle period of relative stability and adaptation, and a final period sometimes characterized by a restlessness and eagerness to conclude the mission that can shade, in difficult seasons with particular interpersonal conflicts, into tension and reduced morale. Extending these patterns from months to decades to centuries is an extrapolation whose results are deeply uncertain, because there is no human experience that provides a reliable guide to what such an extension would produce. But we can make some thoughtful observations based on what we know about the psychology of long-term isolation, the sociology of small communities, and the dynamics of institutional purpose and cultural continuity across generations. Small, isolated communities of human beings tend to develop intense internal social dynamics, a concentration of attention and emotional investment on the people and relationships immediately present. In the absence of the broader social context that normally distributes this attention across a much wider network of relationships, this concentration can be both a strength, producing deep bonds, strong mutual support, and intense team cohesion, and a vulnerability, because the same intensity that creates strong bonds also makes interpersonal conflicts more impactful and harder to resolve. In the confined environment of a spacecraft, with no possibility of simply walking away from a difficult relationship, interpersonal tensions that would be minor irritants in a larger social context become significant challenges to operational effectiveness and crew well-being. The management of interpersonal dynamics in small, isolated crews is one of the most actively studied aspects of long-duration space mission psychology, and the research consistently identifies it as one of the most critical factors in mission success. For a multi-generational journey, one spanning not one, but many human lifetimes, the social challenges would evolve in ways that are difficult to fully anticipate. The founding generation, who chose to undertake the journey and who carry the original motivation and purpose in their personal experience, would be succeeded by a generation that never chose the mission and never knew any other life. A generation born into the spacecraft, knowing nothing of the Earth or the civilization that launched the mission except what they are taught and what is preserved in the ship's records and traditions. The question of what gives this second and subsequent generation a reason to maintain the mission, to continue caring for the ship and its systems, to transmit the necessary knowledge and skills to their own children and prepare them in turn for the responsibilities of the journey. This is not an engineering question, but a deeply human one. A question about the sustainability of purpose and meaning across generations. Human civilizations on Earth have sustained long-term projects across generations. The construction of medieval cathedrals, the maintenance of religious and cultural traditions over centuries and millennia, the slow accumulation of scientific knowledge across the lifetimes of thousands of individual researchers. But these multi-generational projects have always been embedded in a much larger and more supportive social context, drawing on the resources and renewal provided by millions or billions of other people not directly involved in the project itself. A generation ship would have no such external support, no fresh influx of perspectives and energy from outside the mission community, no possibility of resupply or reinforcement from the broader civilization. The sustainability of purpose across generations in such a setting is genuinely uncertain, and the history of isolated human communities on Earth, colonies cut off from their parent societies, communities trapped by geography or circumstance from outside contact, suggests that cultural drift, the gradual loss of original purposes, and the emergence of new and unplanned cultural forms is a nearly universal feature of long-term isolation. The preservation of technical knowledge is perhaps the most immediately critical practical dimension of this generational challenge. The operation of a complex interstellar spacecraft would require a vast library of technical knowledge distributed across many disciplines: propulsion engineering, life support systems, medical care, navigation, communications, materials maintenance, computer systems, all of which would need to be preserved, taught, and actively practiced with fidelity across each generational transition. On Earth, the preservation of technical knowledge is supported by writing, by institutions, by the large numbers of practitioners in any given field, by the continuous stream of new students and researchers who encounter and renew the knowledge, and by the ability to rebuild or redevelop lost knowledge using the resources of a large and diverse civilization. A generation ship community would have only a fraction of these supports. Written records and whatever educational structures could be maintained within a small community, and the loss of critical knowledge through the attrition of generations, through the gradual contraction of the educational system as the community focused on more immediately pressing concerns, or through the simple drift of cultural priorities, could have irreversible consequences. There is also a quieter philosophical dimension to the generational challenge, one that has no immediate practical implication, but that is worth sitting with in the reflective spirit of this evening's journey. The people born on the generation ship in the middle of the crossing, neither the founding generation who chose the journey nor the arrival generation who will see its completion, would inhabit a life whose entire arc from birth to death would take place in transit, in the in-between. They would never know the civilization that launched the mission and would not live to see the destination. They would exist entirely in the journey itself, without origin or arrival in any personal sense, their lives complete within a context that was defined entirely by movement and by the purpose and values of a community they were born into without consent. This is, in a sense, an extreme version of the existential situation that all human beings inhabit. We are all born into a world and a moment we did not choose, embedded in a history we did not make, and a future we will not see in full, finding meaning and purpose within the span of our own lives while participating in projects and communities that extend far beyond that span. But the intensification of these features in the generation ship scenario, the small scale of the community, the total enclosure of the environment, the absolute dependency on the mission's success for personal survival, the impossibility of exit or withdrawal. makes the existential demands on the individual much more concentrated and much harder to escape or manage through the ordinary strategies of a life embedded in a large and diverse society. Philosophy and literature have engaged with these questions in various ways and from various angles. The nature of personal identity and continuity across time. The ethics of bringing beings into existence in conditions they did not choose. The sources of meaning and purpose in lives lived without the prospect of personal completion of the larger project to which they contribute. These are not merely abstract philosophical puzzles, but gently practical questions whose answers would matter enormously to the well-being and cohesion of any real multi-generational space community. The development of a philosophical and cultural framework adequate to the demands of such a journey, one that could sustain a coherent and humane community across many generations of deep space travel, would itself be one of the most challenging and important aspects of the mission, perhaps more challenging in some ways than any of the engineering problems, because the solutions would need to be living and adaptive rather than fixed and mechanical, responsive to the evolving needs and experiences of each generation, while maintaining continuity with the original purpose. Let us now take a step back from the specific challenges and look at the larger picture that they compose together. We have spent a long and patient evening exploring the distances involved in a galactic crossing, the physics of travel at relativistic velocities, the biological vulnerabilities of the human body in deep space, the structure and character of the interstellar environment, the engineering requirements of propulsion and power, and the psychological and social dimensions of long-duration isolation. What emerges from this exploration is not a single decisive obstacle, but a constellation of interconnected challenges, each one significant in itself, all of them amplifying each other in ways that together produce a picture of a journey, gently but thoroughly, beyond the current and foreseeable capabilities of human civilization. What is perhaps most quietly remarkable about this picture is not the impossibility it suggests, but the precision with which we can describe it. Every one of the challenges we have explored is known to us because of the work of thousands of researchers across multiple disciplines, working over decades and generations, accumulating knowledge through careful observation and experiment and theory, building models of the galaxy's structure and of human biology, and of the physics of high-speed travel that are detailed and reliable enough to allow us to make specific, quantitative statements about what the challenges would be. We cannot cross the galaxy, but we can describe with considerable accuracy why we cannot cross it, and that description is itself a kind of crossing, a journey made in the mind rather than in space, a traversal of the galaxy achieved through understanding rather than through motion. The capacity to understand the universe at scales vastly larger than the scale of human life is perhaps the most extraordinary thing about the human mind. The universe did not arrange itself for the convenience of human comprehension. The distances between galaxies, the timescales of stellar evolution, the energies involved in black hole accretion and supernova explosions, none of these were calibrated to human perception or cognition. They are what they are by virtue of the physical laws and initial conditions of the universe, and they are, most of them, far outside the range of direct human experience. And yet, the human mind, this few kilogram collection of neurons and synapses and electrochemical gradients, this biological computer that evolved to navigate the social and physical challenges of life on a single small planet, has managed, through the accumulated effort of countless generations of curious individuals, to understand the structure of a galaxy 100,000 light-years across, to measure the mass of a black hole 4 million times heavier than the Sun at a distance of 26,000 light-years, to map the distribution of dark matter through its gravitational effects across structures spanning billions of light-years. This is not a small thing. It is, on reflection, a quietly extraordinary thing. The kind of thing that rewards extended, patient contemplation rather than passing acknowledgement. The same species that cannot survive a journey across the Milky Way can nonetheless comprehend the Milky Way in detail sufficient to explain why the journey is not survivable. And there is something gently beautiful about that asymmetry, something that speaks to a unique and perhaps irreplaceable quality of conscious, curious beings embedded in a universe that far exceeds their physical reach. The history of science is, among other things, a history of this gradual extension of human understanding beyond the boundaries of human experience. From the moment when ancient astronomers first realized that the lights in the sky were not simply decorations on a celestial dome, but objects at various distances, moving according to regular and discoverable rules. The project of extending human understanding outward has proceeded in a long, slow, patient arc. The arc has bent, sometimes steeply, sometimes almost imperceptibly, in the direction of comprehension. Each generation building on the last, each new instrument or theoretical insight opening a new range of phenomena to investigation. Each answer producing a fresh set of questions that called for further observation and further thought. The current picture of the Milky Way that we have slowly assembled together during this evening is itself a product of this historical process, layered with contributions from every era of astronomical investigation. The ancient Greeks who named the galaxy, the Renaissance observers who first turned telescopes to the sky and resolved the Milky Band into individual stars, the meticulous star-counting observers of the 18th and 19th centuries who tried to map the shape of the stellar system and were misled by dust they did not yet know about. Shapley, who discovered the true position of the Sun within the galaxy using globular clusters as his guide. Hubble, who resolved the nature of the spiral nebulae and established the true scale of the universe. The radio astronomers of the mid-20th century who mapped the spiral structure of the Milky Way using the 21-centimeter emission of neutral hydrogen, the only radiation that could penetrate the dust-obscured plane of the disk. The infrared and X-ray and gamma-ray astronomers who revealed new layers of the galaxy's structure invisible at optical wavelengths. The theorists who developed the framework of general relativity and applied it to the dynamics of galactic centers, predicting the properties of supermassive black holes decades before the observational evidence became available to test those predictions. The engineers and scientists of the Event Horizon Telescope collaboration, who converted a planet-spanning network of radio dishes into a single instrument capable of imaging the shadow of Sagittarius A star, with the resolution necessary to see a feature the size of a large star at a distance of 26,000 light-years. All of these contributions, made by people who were mortal, who had limited lifespans and limited resources, who could not travel to the places they were studying, who had to work with the instruments and the data and the institutional support available to them in their own time and place. All of these contributions together produced the picture we have. And the picture we have, while the most detailed and carefully tested model of the galaxy ever assembled, is still in every important sense incomplete. There are open questions at every level of description, from the detailed structure of the interstellar medium in specific regions of the disk, to the nature of the central mass, to the origin and properties of dark matter, to the long-term dynamical future of the galaxy, as it slowly evolves and eventually merges with Andromeda over the next few billion years. This incompleteness is not a failure of science, but a feature of it. The permanent presence of open questions is what keeps the project of understanding alive and moving forward. What ensures that there is always more to explore, always another layer of the onion to gently peel back, always another quiet surprise waiting in the data. Science does not move toward a point of completion where all questions are answered and the project concludes. It moves toward increasing precision, increasing comprehensiveness, increasing confidence in its most carefully tested conclusions, while always encountering new phenomena and new questions that open fresh areas of investigation. The universe, in this sense, is an endlessly generous collaborator, always providing more complexity and more subtlety than any model fully captures, always quietly exceeding the reach of any description. For the Milky Way specifically, the coming decades promise continued refinements in our understanding at every scale. The Gaia mission, the European Space Agency's extraordinary astrometric satellite that has measured the precise positions, distances, and motions of more than 1 billion stars, is producing a three-dimensional map of the Milky Way's structure in the solar neighborhood with a precision that was unimaginable before its launch, revealing the complex, rippled structure of the disk, the subtle signatures of ancient merger events encoded in the motions of halo stars, and the detailed kinematic properties of stellar populations that allow their formation histories to be traced backward through time. Future large-scale surveys of the sky, both from the ground and from space, will extend this three-dimensional census of the galaxy to larger distances and fainter objects, filling in the picture of the outer disk and halo with a level of detail that current data only hints at. Radio interferometry, the technique used to image Sagittarius A star, will continue to improve in sensitivity and resolution as more telescopes are added to the network and as processing algorithms become more sophisticated, potentially allowing the detailed study of the dynamics of gas and stars in the immediate vicinity of the galactic center, with a precision that would have seemed simply impossible a generation ago. Gravitational wave observatories, instruments like LIGO and Virgo, which detect the ripples in space-time produced by merging black holes and neutron stars, will accumulate statistics on the population of compact objects throughout the galaxy, providing information about the end states of stellar evolution and the distribution of the most extreme concentrations of matter. Future space-based gravitational wave detectors, sensitive to lower frequencies, and thus to larger and more distant sources, will extend this census to the massive black holes at galactic centers and provide new ways to probe the properties of space-time in the most extreme gravitational environments. The question of dark matter, perhaps the deepest and most persistent open question in our understanding of the galaxy and of the universe as a whole, continues to motivate both observational and theoretical investigation on many fronts. Direct detection experiments, searching for the faint nuclear recoils that dark matter particles might produce in ultra-sensitive detectors, buried deep underground to shield them from cosmic ray backgrounds, have been growing steadily in sensitivity without yet detecting a positive signal. Indirect detection searches, looking for the gamma rays or other radiation that might be produced by the annihilation or decay of dark matter particles in regions of high dark matter density, like the galactic center or dwarf galaxies, have found various intriguing anomalies that may or may not prove to have a dark matter explanation. Collider experiments at the Large Hadron. Collider and its future successors search for dark matter particles produced in high-energy collisions, probing mass ranges and interaction strengths that direct and indirect searches cannot easily access. And theorists continue to develop and refine the models that might explain what dark matter is and why it exists, from the lightest possible options to the most exotic, from supersymmetric partners of known particles to primordial black holes, to entirely new kinds of fields and forces that do not fit into any existing theoretical framework. The gradually evolving understanding of dark matter, whatever its eventual resolution, will have significant implications for our picture of the Milky Way and for the galaxy's place in the broader cosmological context. Dark matter is the dominant component of the galaxy's mass. If we could suddenly understand it, detect it, characterize it in the way we characterize ordinary matter, the picture of the galaxy we have assembled would be enriched by the addition of an enormous and currently invisible component whose distribution and dynamics we could trace with the same precision we currently apply to the visible stars and gas. The galaxy would become, in a sense, more fully itself, its complete structure more accessible to investigation, its history more completely readable. And perhaps most intriguing of all, the question of life in the galaxy, of whether the chemistry and physics of the Milky Way's billions of stellar systems have produced, somewhere in the interstellar distances, other minds looking out from other planets at the same band of soft light crossing their sky, remains as open and as gently compelling as it has ever been. The detection of exoplanets, planets orbiting stars other than the Sun, has transformed from a theoretical possibility to an observational routine in the past 3 decades, with thousands of confirmed exoplanets now catalogued, and the statistical inference strongly suggesting that essentially every star in the galaxy hosts at least one planet, and that a significant fraction of stars host planets in the range of sizes and orbital distances compatible with the existence of liquid water at the surface. Whether any of these billions of potentially habitable worlds actually harbor life, simple or complex, microbial or intelligent, capable of looking up at its sky and wondering what lies beyond, remains unknown. The search for biosignatures in exoplanet atmospheres, the detection of gases that would only be present in significant quantities if biological processes were producing them, is one of the most active frontiers of current observational astronomy, and future space telescopes with larger mirrors and more sophisticated spectrographs will push this search much further, potentially detecting the atmospheric fingerprints of photosynthesis or anaerobic metabolism on planets orbiting nearby stars. Whether any signal of intelligence, a radio broadcast, a laser pulse, a structured pattern in some wavelength of the electromagnetic spectrum, lies waiting in the data of some future large-scale sky survey is a question that no one can answer with confidence. And that carries with it the quiet weight of one of the most profound open questions in all of human knowledge. If other minds do exist, somewhere in the 100,000 light-years of the Milky Way, the same physics that limits our ability to cross the galaxy limits theirs as well. The speed of light constrains any signal, any message, any communication to travel no faster than light itself, which means that any exchange of information between civilizations separated by the distances typical of the galaxy would unfold over timescales of hundreds to thousands of years. The messages drifting across the interstellar medium at the maximum speed the universe allows, arriving at their destinations long after the moment that prompted them. The universe constrains not only the physical crossing, but the communicative one, ensuring that even the most advanced and long-lived civilizations would be separated by profound distances of time as well as space. This is a fact worth contemplating with equanimity rather than regret. The distances of the galaxy are not a failure of design or a cruel imposition. They are simply what the universe is, the natural consequence of the physics and the history that produced the cosmos we inhabit. Gravity gathered hydrogen into galaxies. Gravity within those galaxies gathered hydrogen into stars. Those stars burned and died and scattered their heavier elements into the interstellar medium, and in the fullness of time, new stars formed from enriched gas, and some of them gathered planetary systems around themselves. And some of those planetary systems produced the conditions in which chemistry became biology, and biology eventually became consciousness. The distances of the galaxy are the same distances that allowed the universe to be old enough for all of this chemistry and geology and biology to unfold. The universe needed billions of years to produce beings capable of asking about the galaxy, and those billions of years of expansion have produced a universe whose scale, measured in light years, dwarfs any biological or even technological timescale. There is something gently clarifying about this perspective. The recognition that the universe's scale and the possibility of life within it are not unrelated features, not independent accidents, but aspects of the same process. We exist in a universe large enough to have required billions of years to produce us, and those billions of years of expansion have made it large enough that we can never cross it in any meaningful sense. The price of our existence, in some sense, is the immensity of the space we exist within. And yet that immensity, even in its utter unreachability, is not alien to us. We carry the universe within us in the most literal sense. The carbon in our cells was forged in the interiors of stars that died before the sun was born. The iron in our blood was produced in the violent terminal moments of supernova explosions, scattered into the interstellar medium, and eventually incorporated into the collapsing gas cloud that formed the solar system. The hydrogen in the water that fills most of our bodies is as old as the universe itself, produced in the first few minutes after the Big Bang, when the cosmos was hot and dense enough for protons and neutrons to fuse into the lightest elements. We are, in the most direct and unmetaphorical sense, assembled from the galaxy, from the materials that stars have made and redistributed over billions of years of stellar evolution. The Milky Way is not simply something we observe from a distance. It is, in a very real sense, where we come from. The atoms in your body have been parts of many things in the long history of the universe. hydrogen in primordial gas clouds, then helium in stellar cores, then heavier elements in successive generations of stellar burning, then dust in the interstellar medium, then molecules in a collapsing gas cloud, then parts of the solar nebula, then rocks and ocean water and atmosphere on the young Earth, then biological molecules in early life, then generations of organisms over billions of years of evolution, and finally, in this particular arrangement, you, sitting or lying comfortably in the late evening, listening to the quiet voice of the cosmos describing itself back to you through the medium of human science and human language. Those atoms have traveled farther in their long history than any spacecraft we could ever build. They have been transformed by processes of a scale and violence and duration that dwarf anything in human experience. And they have, at this moment in their long journey through the universe, assembled themselves into a form capable of understanding and appreciating the journey they have taken. There is something quietly remarkable about that. Not loud, not dramatic, not designed to impress or to startle. Simply gently, genuinely remarkable. The universe has produced, in at least one place that we know of, arrangements of matter complex enough to look back at the universe and ask how it works, to measure its structures and trace its history and understand something of the laws that govern its behavior. Whether this has happened in other places is unknown. Whether it will continue to happen is unknown. Whether the understanding that conscious beings accumulate about the universe serves any purpose larger than the conscious beings themselves is a question that philosophy and science together cannot currently answer. But that it has happened, that matter has organized itself into minds, that the galaxy we can never cross has nevertheless been comprehended in broad and deepening outline by the minds it produced. This is a fact that rewards quiet reflection. As we approach the end of this long, slow evening journey, let us allow the mind to drift for a moment, as it does when sleep begins to approach, in the direction of the simply beautiful rather than the specifically explanatory. The galaxy we have explored tonight, the 100,000 light-year spiral of gas and stars and dust and dark matter, slowly rotating in the darkness of intergalactic space, its spiral arms traced by the brilliant fires of young stars, and its ancient central bulge glowing with the quiet light of stars born before the solar system existed. This galaxy has been turning since it formed, roughly 13 billion years ago, in the early aftermath of the Big Bang. It has turned 50 or 60 times in the time since the first stars ignited within it. It has produced generation after generation of stars and swept their material back into the interstellar medium and made new generations from the enriched remnants, slowly building up the chemical complexity that eventually made planets and life possible. All of this has happened in silence, from a human perspective, in the silence of deep time and deep space, unwitnessed until conscious beings arose within it and began to notice and to measure and to understand. The galaxy did not need to be witnessed to exist, and it does not need to be understood to function. Its dynamics and its evolution proceed according to the same physical laws, whether or not any mind in it takes note of them. But there is something that happens when a mind does take note. A kind of completion, a kind of closure, as the universe begins to know itself through the awareness of the beings it has produced. The galaxy looks back at itself through your eyes tonight, and through the patient accumulation of knowledge that lies behind what has been shared in this long evening. It does not need this self-knowledge to be what it is, but the fact that it has it, the fact that you exist and are awake enough to this slow and quiet science to have spent these hours in its company is, in the gentlest and most unhurried sense, one of the more extraordinary things the universe has yet managed to arrange. The crossing we have explored tonight will not be made by any human being in any lifetime anyone now living will see. The distances are too great, the challenges too deeply woven into the fabric of physics and biology. But the crossing of understanding, the slow, patient, multi-generational journey of comprehension that has taken us from Galileo's first telescopic glimpse of the Milky Way's individual stars to the Event Horizon Telescope's image of Sagittarius A star, from Herschel's star counts to Gaia's billion-star map, from Kant's philosophical speculation about island universes to Hubble's definitive measurement of the distance to Andromeda. This crossing is one that human beings have been making together for a very long time, and it continues tonight and tomorrow night, and in every observatory and laboratory and classroom and quiet evening conversation where someone allows their mind to settle into the scale and the wonder of the cosmos, and to simply patiently understand a little more of it than they did before. The galaxy will be there when you wake. Its slow rotation, its patient stellar generations, its dark matter halo, and its ancient globular clusters and its mysterious central mass, all of it will continue, quietly and without urgency, as it has for 13 billion years. You do not need to hold it in your mind tonight. You can let it go, gently, into the soft darkness of sleep, knowing that it will be there when you return to it, knowing that the questions it raises will keep, knowing that the universe is patient in a way that only something 13 billion years old can be patient. Good night, and welcome back to the continuing quiet of this long evening together. This slow and unhurried drift through the science and the wonder of the galaxy we call home. We have traveled far tonight in the imagination, and yet there is always a little more to say. Always another gentle layer to unfold. Always one more thread in the vast tapestry of the Milky Way that deserves a moment of patient attention before the night fully closes in. So let us continue, softly and without urgency, as the stars continue their slow revolutions overhead. Consider, for a moment, the nature of light itself, that most fundamental of messengers, the medium through which virtually all of our knowledge of the galaxy has arrived. Every photon that has ever entered a telescope and contributed to our picture of the Milky Way has traveled through the interstellar medium for years or centuries or thousands of years before reaching us, carrying in its wavelength and its polarization and its timing information about the conditions at its point of origin. The light from a star 26,000 light-years away, the same distance as the galactic center, left that star 26,000 years ago, when human beings were still living exclusively as hunter-gatherers, painting animals on cave walls and navigating the landscape by the stars themselves. We see the galactic center not as it is now, but as it was when the last ice age was still reshaping the northern hemisphere. Every observation of the distant galaxy is, in this sense, an act of archaeology, a reading of the past written in light. This time-lagged quality of astronomical observation is one of the most quietly remarkable features of the science, and it gives the Milky Way a kind of temporal depth that a map can only hint at. When we look at the outer edge of the galaxy 50,000 light-years away, we see light that departed those distant stellar neighborhoods 50,000 years ago. Before the development of agriculture, before any recorded language, before the construction of any monument that has survived to the present day. When we observe a galaxy in the Virgo cluster 60 million light-years away, we see it as it was when the dinosaurs were still alive on Earth. The universe, observed through telescopes, is a layered archive of its own past, and the further we look in space, the further back in time we see. Looking outward and looking backward in time are, for astronomers, the same act. This is a feature of the universe that has no direct analogue in ordinary human experience, and it requires a gentle recalibration of intuition to fully appreciate. When you look at a friend's face across the room, the light reflected from their face takes approximately 10 nanoseconds to reach your eyes. A delay so infinitesimally small as to be entirely irrelevant to ordinary perception. When you look at the sun, the light is 8 minutes old. When you look at the nearest stars, it is years old. When you look at the band of the Milky Way overhead, the light from its most distant parts is tens of thousands of years old. And when you look at the faint smudge of the Andromeda galaxy on a clear, dark night, the light entering your eye left Andromeda 2.5 million years ago, before the emergence of the genus Homo on Earth. The night sky is not a snapshot of the present. It is a composite image assembled from light that departed its sources at many different moments in the deep past, a tapestry of history woven from photons that have been traveling toward this moment for spans of time, ranging from minutes to billions of years. The Milky Way's own history, as it can be reconstructed from the properties and motions of its stars, is a story of gradual assembly and calmly evolving complexity. The galaxy did not appear fully formed in its current state. It grew over billions of years through a combination of the slow infall of gas from the surrounding intergalactic medium and the gradual accumulation of smaller structures, dwarf galaxies and proto-galactic fragments, drawn together by gravity into the large, organized spiral we inhabit today. The oldest stars in the galaxy's halo, some of them older than 12 billion years, among the oldest objects in the observable universe, formed in the earliest epochs of the galaxy's existence, when the gas reservoir was still largely pristine hydrogen and helium, before the many stellar generations that would enrich it with heavier elements had run their course. These ancient stars are chemical time capsules, preserving in their spectral signatures the abundance patterns of the early galaxy, allowing astronomers to read something of the conditions that prevailed when the Milky Way was still young and the cosmos as a whole was only a few billion years old. The thick disk, as we mentioned earlier, formed in a period of the galaxy's history when the star formation rate was higher and the disk geometrically less settled, producing a stellar population with intermediate ages and chemical compositions that reflect the enriched but still relatively metal-poor conditions of that early epoch. The thin disk, the flat, well-organized disk in which the Sun and most of the galaxy's current star formation reside, formed later as the gas that had not yet been converted to stars settled into a thinner, more rotationally organized configuration. The Sun itself, at roughly 4.5 billion years of age, is a third-generation star. It formed from gas that had already been processed through at least two earlier generations of stellar evolution, which is why it contains a rich endowment of heavy elements compared to the oldest stars in the galaxy. Our solar system, and everything within it, including the Earth and all life upon it, owes its chemical complexity to those earlier stellar generations. The long-dead stars whose supernova explosions scattered carbon and oxygen and nitrogen and iron and all the other heavy elements into the interstellar medium and eventually into the collapsing cloud that became the Sun. The future of the Milky Way is written in broad outline by the same gravitational physics that has governed its past. The most significant event in the galaxy's foreseeable future is the merger with the Andromeda Galaxy, our nearest large neighbor, currently approaching us at roughly 110 kilometers per second, on a trajectory that will bring it into gravitational interaction with the Milky Way in approximately 4 billion years, and into a full merger over the billion or so years following that initial close encounter. The merger of two large spiral galaxies is not a violent or catastrophic event in any human sense. The stars within each galaxy are so sparsely distributed that actual stellar collisions during the merger would be extraordinarily rare, and the dominant effects would be gravitational, scrambling the organized spiral structures of both galaxies and eventually settling into a new, larger, roughly elliptical galaxy that astronomers have taken to calling Milkomeda. The gas clouds of both galaxies, however, would collide and compress, triggering intense bursts of new star formation as the merger proceeds, a final flowering of stellar creation before the merged system settles into a quieter old age. By the time the Milky Way and Andromeda begin their long gravitational embrace, the Sun will be in the late stages of its own evolution, swelling into a red giant, expanding outward to engulf the inner planets and scorching the surfaces of whatever remains of Earth and Mars, before shedding its outer layers as a beautiful planetary nebula and leaving behind a slowly cooling white dwarf. The Sun's fate is not exceptional. It is the standard fate of a solar mass star, the same quiet end that awaits the vast majority of the stars currently burning in the Milky Way. The galaxy's long stellar history will continue in its descendants, the dim red dwarfs, the white dwarfs cooling slowly in the dark, the neutron stars spinning in silent isolation, long after the last solar mass stars have exhausted their fuel and faded. On the longest timescales so long that even the word timescale begins to feel inadequate, the fate of the galaxy and the universe trends toward a kind of quiet dissolution. In the far future, measured in trillions and quadrillions of years rather than billions, the remaining stars will burn out one by one, the red dwarfs lasting the longest before finally exhausting their fuel, and the galaxy will become a dark collection of stellar remnants, white dwarfs, neutron stars, black holes, slowly losing energy to gravitational wave emission, and eventually, over almost incomprehensibly long timescales, spiraling inward toward the central black hole or dispersing through gravitational interactions into intergalactic space. The protons that make up the matter in all of these objects may themselves eventually decay, on timescales orders of magnitude longer still, leaving behind nothing but radiation and the lightest particles. The universe's future, on the very longest view, is one of calmly deepening quiet. This is not a melancholy thought, though it might sound like one. It is simply the natural arc of a universe governed by the laws of thermodynamics, laws that are as beautiful in their precision and their universality as any in physics. The universe began in a state of very low entropy, very high order in the specific physical sense that its energy was concentrated in a hot, dense, uniform state. And it has been moving ever since in the direction of increasing entropy, distributing that energy more and more evenly across an ever larger volume of space. The stars and the galaxies and the planets and the life that has arisen on at least one of those planets are all, in a sense, eddies in this great river of entropy. Local, temporary concentrations of order and complexity that persist for a while, sustained by the flow of energy from hot sources to cold sinks, before eventually dissolving back into the surrounding equilibrium. The brief, brilliant burning of the stars, the slow assembly and evolution of galaxies, the emergence of life and consciousness on small rocky worlds. All of these are flowers that bloom in the flow, beautiful precisely because they are temporary, meaningful precisely because they are local concentrations of order and complexity in a universe trending toward uniformity. The human experience of meaning, of beauty, of connection and understanding, all of these arise in the space created by this thermodynamic flow, in the energy gradient between the sun's burning core and the cold darkness of space that allows chemistry and metabolism and neural activity to occur. Remove the gradient and the flow, and there is no life, no thought, no appreciation of the galaxy's grandeur. The very fact that we can sit here tonight and contemplate the Milky Way, that we can feel something like wonder at the 100,000 light years of slowly rotating starlight, that we can understand why it cannot be crossed in any human lifetime, and find that understanding quietly beautiful rather than simply frustrating. All of this depends on the same thermodynamic process that will eventually, in the very long run, erase everything we have built and thought and felt. And yet, that eventual erasure does not diminish the meaning of the present moment. It may, on careful reflection, be what gives the present moment whatever meaning it has. The practice of astronomy itself, the patient, careful, multi-generational project of understanding the universe, is one of the more quietly beautiful things that human beings have ever engaged in. It is a practice that requires the suspension of urgency, the willingness to work on questions whose answers will come slowly and partially, and often not within the lifetime of the person posing them. It requires humility, the ability to hold one's current best understanding lightly, knowing that better data or a new theoretical insight may require it to be revised or discarded. It requires a kind of love for the subject that does not depend on the subject returning that love, a willingness to devote attention and care and intellectual effort to objects and processes that are completely indifferent to the observer's existence. These are, in a sense, the same qualities that make any form of deep attention and quiet care valuable in human life. Whether it is applied to the stars, or to the garden, or to the people we love. The astronomers whose work underlies everything shared in this long evening were, each of them, human beings living human lives, dealing with the ordinary challenges and pleasures and difficulties of embodied existence on this small planet, going to sleep at night under the same stars they spent their days measuring and thinking about, carrying within them the same uncertainties and longings that all human beings carry, finding in the practice of their science something that was, for each of them in their own way, a source of meaning and satisfaction that went beyond the mere accumulation of facts. Shapley, tracking globular clusters with Mount Wilson's Great Mirror, trying to determine where in the galaxy he and everyone else was located. Hubble, measuring the recession velocities of distant galaxies and discovering, almost accidentally, that the universe was expanding. Vera Rubin, whose careful measurements of galaxy rotation curves in the 1970s provided some of the most compelling early evidence for the existence of dark matter. Evidence that emerged not from a dramatic discovery, but from a quiet, patient, methodical program of observation that showed, in galaxy after galaxy, that the stars at the outer edges were moving too fast for the gravity of the visible matter to explain, that something else, something invisible and abundant, must be filling the halos of galaxies and providing the additional gravitational influence needed to keep the fast-rotating outer stars in their orbits. Each of these scientists worked in the context of their own time and place, with the instruments and the theoretical frameworks and the scientific culture available to them. And each of them made contributions that they could not fully evaluate in their own lifetimes, because the significance of a discovery often becomes clear only in retrospect, only after subsequent researchers have built upon it and extended it and revealed its connections to other pieces of the puzzle. This is one of the most quietly distinctive features of scientific knowledge. It is genuinely cumulative in a way that few other human endeavors are, each generation inheriting and building upon the verified findings of all previous generations. No knowledge lost that has been carefully established, no insight wasted that has been correctly understood. The knowledge we now have of the Milky Way is the inheritance of all of those patient observers and theorists, accumulated over 4 centuries of telescopic astronomy and a somewhat longer tradition of careful naked eye observation before that. It is a knowledge that continues to grow, gently and continuously, as new instruments come online and new analyses are performed and new theoretical ideas are developed and tested. The picture we have tonight is more detailed and more accurate than the picture that existed 10 years ago, and less detailed and accurate than the picture that will exist 10 years from now. This is not a limitation, but a promise, the assurance that the work of understanding continues, that the questions we currently cannot answer will be approached with better tools and better frameworks in the future, that the story of the Milky Way is not a finished story, but a calmly evolving one. Some of the most interesting questions about the Milky Way that currently remain open are questions not about the galaxy's large-scale structure, which is now reasonably well characterized, but about the detailed processes operating within it. How does star formation work in detail? We understand the broad outlines. Dense cores within molecular clouds collapse under gravity, spinning up as they contract and flattening into protostellar disks from which planets eventually form. But the details of what triggers collapse, how the initial conditions of the collapsing core determine the mass and properties of the star that forms, how feedback from the forming star itself affects the surrounding cloud and the formation of sibling stars, remain areas of active research with important open questions. These are questions whose answers require not just observational data, but the development of increasingly sophisticated numerical models of the complex hydrodynamic and magnetic processes operating in star-forming regions. simulations that run on the world's most powerful supercomputers for weeks or months to reproduce the formation of a single stellar system. How does the Milky Way's magnetic field, the large-scale magnetic field threading through the interstellar medium and influencing the dynamics of gas and cosmic rays throughout the disk, connect to the small-scale magnetic fields associated with individual stars and star-forming regions? How does the magnetic field affect the efficiency of star formation, the propagation of cosmic rays through the galaxy, the structure of the interstellar medium at different scales? These questions, belonging to the field of galactic magnetism, are ones whose answers require radiopolarimetry observations of unprecedented sensitivity and coverage. Observations that are becoming possible with new and planned radio telescope arrays, but whose full scientific implications are still being worked out. How did the first stars form in the early universe before the interstellar medium had been enriched with any heavy elements? These first stars, called population 3 stars, formed from gas that was essentially pure hydrogen and helium, without the cooling provided by the complex molecules and dust that assist star formation in the modern interstellar medium. Theoretical models suggest that these first stars were likely much more massive than typical modern stars, perhaps hundreds or even thousands of solar masses, and that they burned for only a few million years before ending their lives in spectacular supernova explosions that seeded the early universe with the first heavy elements. None of these first-generation stars survive in the Milky Way today. They lived and died too quickly. But their influence is encoded in the chemical compositions of the oldest surviving second-generation stars, the most ancient stars in the galaxy's halo, whose abundances of heavy elements reflect the specific mix of elements produced by the supernova of their first-generation predecessors. The search for these ancient, chemically primitive stars, stars whose chemical compositions carry the clearest imprint of the earliest stellar generation, is an active area of observational astronomy, and the stars found at the extreme metal-poor end of the distribution have yielded extraordinary insights into the conditions of the early universe. Some of these stars show chemical abundance patterns that match remarkably well with the predicted yields of specific types of early supernova, pair instability supernova, or hypernova explosions of rotating massive stars, providing a kind of chemical fossil record of individual early stellar deaths, preserved across more than 12 billion years in the spectra of surviving second-generation stars. This is time archaeology on a scale that has no terrestrial analogue, reading the record of individual events from the universe's first billion years in the light of stars we can observe tonight. The exoplanet revolution, the discovery and characterization of planets orbiting other stars, which has transformed from a speculative possibility to an observational routine in the past 3 decades, has added a new dimension to our understanding of the Milky Way as a habitat. We now know, with high statistical confidence, that the galaxy contains at least as many planets as stars, and likely significantly more. Rocky planets, the most potentially habitable type, appear to be extremely common around the most numerous class of stars, the small and long-lived red dwarf stars that make up perhaps 70% of all stars in the galaxy. Many of these rocky planets orbit in the habitable zones of their host stars, the range of distances at which liquid water could exist on the surface under appropriate atmospheric conditions, and a growing number have been identified as potentially interesting targets for the study of atmospheric biosignatures. The characterization of exoplanet atmospheres is still in its early stages. Even the most sensitive current instruments can only detect the strongest and most distinctive atmospheric features of the most favorable targets. But the trajectory of development is clear and calmly promising. The James Webb Space Telescope, launched in late 2021 and now operating with extraordinary sensitivity at infrared wavelengths, has already begun to probe the atmospheres of some exoplanets with a precision that previous telescopes could not approach, detecting the presence of carbon dioxide and water vapor and other molecules in the atmospheres of giant planets, and beginning to examine the atmospheres of smaller rocky worlds. Future missions, both ground-based extremely large telescopes and planned space telescopes with apertures significantly larger than Webb's, will push this characterization to smaller planets and fainter biosignature signals, with the genuine possibility of detecting the first unambiguous evidence of biology beyond Earth within the coming decades. What would it mean to find such evidence? To discover that the chemistry of life had arisen independently in some other corner of the galaxy, on some distant world orbiting some quiet red star, assembling itself from the same raw materials that were available in the early solar system, and producing some form of biological complexity that had left its mark in the atmospheric chemistry detectable from 20 or 30 light-years away. It would be, in the simplest terms, one of the most profound discoveries in the history of human knowledge. A quiet but enormous shift in our understanding of our own place in the cosmos. A confirmation that the emergence of life is not a singular accident, but a recurring theme in the universe's chemistry. It would not be a loud or dramatic moment. It would most likely arrive as an anomalous spectral signature in a dataset, requiring careful verification and analysis and independent confirmation before the scientific community accepted it as genuine, the excitement building slowly and methodically, rather than announcing itself with a sudden revelation. And even that discovery would leave most of the deepest questions unanswered. Whether the life was simple or complex, whether it had developed anything like intelligence or communication, whether it knew of our existence or cared, whether it had looked outward from its own world and wondered about the galaxy it inhabited and the possibility of minds elsewhere within it. These questions might never be answerable, depending on the nature and distance of the biological signal. They would simply hang in the air as the best scientific discoveries tend to do, resolving one question while opening a dozen new ones, expanding rather than closing the frontier of what remains to be understood. The Milky Way, in the end, is a place of extraordinary richness, not a barren wilderness of empty space, but a vast and structured ecosystem of matter and energy, of stellar births and deaths and rebirths, of chemical evolution and gravitational dynamics and magnetic fields and cosmic rays, and the slow, patient churning of gas into stars and planets. And, in at least one case we know of, into beings capable of awareness and curiosity, and the particular kind of love that finds expression in the patient, careful study of the cosmos. It is a place we cannot cross, but a place we deeply and genuinely inhabit, whose history is our history, whose material is our material, whose slow evolution has been, in a very real sense, the setting in which everything we are and everything we know has come to be. The 100,000 light-years that separate one edge of the galaxy from the other are not a barrier between us and something else. They are the extent of our home. A home too large to walk across, but not too large to know or to love, in the only way that minds like ours are capable of loving the immensities we find ourselves within, which is the quiet, sustained, endlessly curious way of understanding. We cannot stand on the far edge of the galaxy and look back, but we can know what is there. We can know what the stars in those distant outer reaches are like, older, cooler, more sparsely distributed. And we can know how the light from those stars was generated in nuclear furnaces and has been traveling across tens of thousands of light years to reach telescopes that human beings built with patient, careful hands. And that knowing, however incomplete it is and will always remain, is its own kind of arrival. The nights are long in the deep parts of the year, and the stars overhead are old, and the galaxy turns slowly enough that a human lifetime is only a fraction of a heartbeat in its great rotation. There is comfort in that, if you let yourself feel it. The comfort of being held within something so much larger and older and more patient than any individual life, of being part of a story whose beginning was before memory, and whose ending is beyond any conceivable future. You do not need to carry the whole story. You only need to inhabit your own small moment of it, to bring to it whatever attention and care and curiosity you have, and to let the rest, the 100,000 light-years, the 4 million solar masses at the galactic center, the dark matter halo extending silently through the space around us, to let all of that simply be what it is, enormous and quiet and indifferent in the most magnificent of ways. The light from the stars will continue to travel after you are asleep. The galaxy will continue to turn. The distant molecular clouds will continue their slow, patient collapse toward the point at which gravity overcomes pressure and a new star ignites. The ancient globular clusters will continue their long orbits around the galactic center, tracing paths they have been following for billions of years. The dark matter will continue to do whatever dark matter does, gravitating, structuring, holding the visible galaxy in its invisible embrace, unmeasured and undetected and present everywhere. All of this will continue without your attention and will still be there, unchanged in any way you could notice when your attention returns to it. And somewhere, in an observatory on a high mountain, or in a room full of servers processing data from a space telescope, a person not unlike you is still awake, looking at a spectrum or a light curve or a set of stellar positions, working patiently toward the next small increment of understanding that will be added to the long cumulative record of human knowledge about the galaxy. That person probably has a cup of something warm nearby, and the quiet sound of fans cooling their computers, and the particular focused calm of someone absorbed in a problem they love. They are, in their own small way, making the crossing tonight, not in space, but in understanding, one careful measurement at a time. You can sleep now. The galaxy will wait. It has been waiting for 13 billion years, and it is very, very good at it. The questions will still be there tomorrow, and the stars will still be there to answer them in their own slow, patient, photon by photon way. Your dreams tonight, if they carry any flavor of what has been shared here, might be full of the soft light of distant stars and the slow spiral of a galaxy too large to cross, but not too large to hold in the mind with a kind of quiet tenderness. Let the numbers dissolve. Let the distances soften. Let the 100,000 light-years fold themselves into the comfortable darkness of a closing evening and become simply the sense, vast, warm, ancient, real, of being held within something unimaginably large that is also, impossibly and gently, home. This has been the sleepy Milky Way. Thank you from the quiet heart of the spiral for spending this long and unhurried evening here. If this journey has brought you any measure of calm, any widening of the inner sky, any sense of the slow and beautiful scale of the cosmos we share, then it has done everything it was meant to do. Subscribe if you would like to make more of these journeys together. There are many more stories waiting in the dark, many more galaxies and nebulae and patient scientific mysteries to unfold at this same unhurried pace, in this same spirit of quiet wonder. Sleep well, traveler. The stars are out, the galaxy is turning, and somewhere, 26,000 light-years from where you lie, the great central mass at the heart of the Milky Way continues its ancient silent vigil. 4 million times the mass of the Sun, wrapped in curved space-time, surrounded by stars moving at fractions of the speed of light, utterly indifferent and utterly magnificent. You are made of the same universe that made it. And tonight, that is more than enough. Good night.